Hello there, and welcome to the Cosmographer. Both of these telescopes were built to answer questions, and this list is the 10 results they could not. Number 9 is a set of water plumes reported erupting from an alien ocean, believed for 13 years and withdrawn in 2026 by the same scientist who found them. Number 6 is 42 pairs of worlds drifting with no sun anywhere in their sky, orbiting each other on 80,000-year timescales, and no model of planet formation or star formation makes them. Number 5 is a galaxy larger than this one that appears to hold no dark matter at all, in a universe where 5/6 of all matter is dark. And number 3 is a count of early galaxies that came out 182 times higher than every model predicted. 10 measurements, 2 telescopes, no accepted explanation, counted down from 10 to 1. Get comfortable and settle in. If quietly working through 10 things the sharpest instruments ever built could not explain sounds like a good night to you, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the one at the top will not be the largest thing here or the furthest away. It will be a simple count that nobody has been able to repeat. Let's begin at number 10. Number 10, the green monster inside Cassiopeia A. There are 2 telescopes above the Earth that have done more to unsettle astronomy than any others ever built. One of them has been returning data since 1990. The other has been returning data since 2022. Between them, they have given us the sharpest optical view and the deepest infrared view of the universe that human beings have ever had, and the ordinary way to describe what they do is to say that they answer questions. That is not quite right. The more accurate description, and the one this list is built on, is that sharpness generates questions. When you resolve something that used to be a smudge, you very often find that the smudge was hiding a contradiction. It was easier to be confident about the universe when the pictures were blurrier. So this is a list of 10 results from those 2 telescopes that survived scrutiny and that nobody has explained. Not 10 mysteries in the loose sense. 10 specific measurements made by specific instruments, published in specific papers, that do not currently have an accepted answer. Some of them are famous. Several of them are almost unknown outside the small groups of people who argue about them. 2 of them have been partly walked back by the very scientists who announced them, and those reversals turn out to be among the most interesting material here. The list climbs. At number 10, the unexplained thing is a set of holes in a cloud of gas around one exploded star. By number 1, the unexplained thing is the shape of the universe itself, and the 2 available explanations are both, in their own ways, worse than the anomaly. Along the way, it passes through a moon, a single star, the space between galaxies, a pair of worlds with no sun, a galaxy missing 5/6 of its mass, and a black hole that appears to have left home. We start 11,000 light-years away, in the constellation Cassiopeia, with the youngest known remnant of an exploded star in our galaxy. Cassiopeia A is the debris of a massive star that tore itself apart, and it is close enough and recent enough that astronomers can watch it move. It spans about 10 light-years, which the European Space Agency renders as roughly 96 trillion kilometers. The distance figure used in the technical literature is 3.4 kiloparsecs, derived not from any single measurement, but from tracking how fast the fastest moving knots of debris are flying outward and working backward. From our point of view, the star exploded about 340 years ago, which raises an immediate problem. Almost nobody saw it. There is no confirmed contemporary record of the Cassiopeia A supernova anywhere in human history. That is remarkable, because an exploding star inside our own galaxy is normally one of the most conspicuous events in the sky. Tycho's supernova in 1572 was recorded across Europe and Asia. Kepler's in 1604 was recorded everywhere. And then a star blew up in Cassiopeia, in the age of telescopes, and the historical record is essentially silent. Working backward from debris that shows almost no sign of slowing down, one analysis derived an explosion date of 1671, plus or minus about a year. But if the debris has been decelerating even slightly, by only 1.5 kilometers per second per year over 3 centuries, the date shifts to around 1680. That matters because on the 16th of August, 1680, John Flamsteed catalogued a star near the remnant's position and labeled it 3 Cassiopeiae. No such star exists there now. Whether Flamsteed logged the supernova or simply made an error in his positions has never been settled, and it depends entirely on a deceleration rate that nobody has measured well. The remnant was not found by eye. It was found by radio, which tells you something about how faint the visible remains had become. Martin Ryle and Francis Graham Smith, working at Cambridge with a long interferometer, reported it in 1948. They had been observing a different radio source in Cygnus when a second discrete source walked into their traces. Cassiopeia A turned out to be among the brightest radio sources in the entire sky outside the solar system, which is to say that one of the loudest objects in the radio universe had been sitting in the constellation Cassiopeia the whole time, and nobody had any way to hear it until then. The optical counterpart came later. Walter Baade and Rudolf Minkowski identified faint filaments on plates taken in 1951 with the 200-inch telescope at Palomar. Then astronomers did something genuinely extraordinary, which deserves to be stated slowly. In 2008, a team led by Oliver Krauser obtained a spectrum of the Cassiopeia A supernova near its maximum brightness. 330 years after the direct light had already swept past the Earth and vanished into the far side of the galaxy, they measured what the explosion actually looked like at the moment it was brightest. They did it with reflections. When a star explodes, the flash travels outward in every direction. Most of it goes off into empty space. But some of it strikes clouds of interstellar dust off to the side, scatters, and comes to us by a longer path, arriving centuries late. Astronomers found those reflections and read the original spectrum out of them. What they read was that Cassiopeia A had been a Type 2b supernova. The star that died had already lost most of its outer hydrogen before it exploded, and what collapsed was a stripped helium core. Models put the original star at 15 to 20 times the mass of the Sun, with only 2 to 4 solar masses of material left to eject by the end. Something had taken the rest of it away. Which brings us to April 2023, and to the picture that produced this item. On the 7th of April that year, Webb's mid-infrared instrument returned a mosaic of Cassiopeia, accredited to Danny Milosavljevic of Purdue, T. Temim of Princeton, and Ilse Deleuze of Ghent. Inside the remnant's interior sat a large green loop that had no counterpart in any previous image, at any wavelength, from any telescope. The team nicknamed it the Green Monster, and the reason is documented in a footnote of the resulting paper. It was named after the tall green wall in left field at Fenway Park. The green is not a real color. It is an artifact of how filters get mapped to a visible image. The emission comes mostly through the 12.8 micron filter, with contributions from the 11.3. But the structure is real. It is large, and in 2023, nobody had any idea what it was. 2 papers in 2024 established the basic identity. combining spectroscopy from two of Webb's instruments with imaging from a third, Deleuze and colleagues associated the green monster with circumstellar material, gas the star had shed before it died, now being lit up from behind. Galaxies, Vink and colleagues reached the same conclusion independently, from Chandra X-ray spectra, and their measurement is precise enough to be worth stating. Every X-ray spectrum along the structure is blue-shifted, corresponding to a velocity of about 2,300 kilometers per second toward us. That places the green monster in front of the remnant, not inside it. It is not part of the explosion. It is the star's discarded outer layers, sitting between us and the debris, and the explosion is illuminating it from the far side. Milosavljevic put it in the plainest possible terms in Purdue's release. Like a rogue photobomber in a vacation photo, he said, the green monster grabbed attention but was not the intended target. His team then digitally removed it from their own image so they could see past it to the faint debris they had actually gone there to study. And that is where the explanation stops, because identifying the green monster as shed stellar gas does not explain the strangest thing about it. The structure is pockmarked. Deleuze and colleagues went through the 11.3 micron image by hand and identified more than 24 near-perfect circular holes, typically 1 to 3 arcseconds across, each ringed by a bright rim only 1/4 to 1/2 arcsecond thick. Something has punched clean through this shell, repeatedly, in circles, and the shell has responded by lighting up around each puncture. There are two candidate mechanisms, and neither has been confirmed. Either small knots of nitrogen-rich debris traveling at 8,000 to 10,500 kilometers per second have outrun the remnant's own forward blast wave, which is only moving at 5 to 6,000, and are punching through the shell ahead of it. Or narrow fingers of debris are protruding into the shocked gas from behind. The team's own written conclusion was that further investigation is needed, which in the language of scientific papers means nobody knows. It is worth stopping for a moment and picturing what that shell would actually be like from the inside, because the numbers alone do not convey it. You are inside a wall of gas that a star threw off tens of thousands of years before it died. It is not glowing on its own. Behind you, the shocked ring of the remnant is pouring out ultraviolet and X-ray light, and that light is raining onto the gas around you and making it answer in the infrared. Milosavljevic described the mechanism exactly that way. The shocked ring shines photons into the cloud that has not yet been shocked, and that is why the interior can be seen at all. So the illumination comes from behind, and it is coming from an event that finished 3 centuries ago. Ahead of you, the wall is punctured. There are holes in it, more than 24 of them, each one a nearly perfect circle a few hundredths of a light year across, and each one ringed by a bright rim of glowing dust. Through the holes you can see the darker interior. The rims are the brightest thing in view, and they are temporary. The grains producing that glow will be eroded away within a single human lifetime, which means the rings you are looking at were made recently, and will be gone soon, and something is still making new ones. And somewhere in the debris behind you, moving at 8,000 kilometers per second or faster, are the objects doing the punching. They look like points of light in Hubble images. They are not points. The average one is around 1,000 astronomical units across, larger than the entire planetary region of the solar system, and it is traveling fast enough to cross the distance from the Earth to the Moon in under a minute. There is a further complication, and it is the kind of detail that makes a problem worse rather than better. The dust in those bright rings should not survive. Deleuze and colleagues estimate that a dust grain 5 nanometers across in that environment is eroded away in roughly 33 years. So the rings we are looking at are either extraordinarily young or they are being continuously remade, and neither option comes with a mechanism attached. The most recent attempt to solve it was published on the 2nd of August 2026, when Salvatore Orlando and colleagues ran three-dimensional simulations of fast knots striking a dense shell. The simulations reproduce the holes only if the knots are relatively slow, at or below 8,000 kilometers per second, and the shell is dense, above about 200 particles per cubic centimeter. Push either parameter, and the holes come out too large. Worse, the simulated structures become significantly distorted within 30 to 60 years of the shock passing through. Their conclusion was that no single mechanism accounts for what Webb sees. The large cavities come from early knots, the compact clean rings from recent first contact punctures, and the older structures from continuous sculpting afterward. That is not one explanation. That is three explanations stacked on top of each other to cover one image. And the object at the center of all this is also strange. The compact remnant at Cassiopeia A's heart was only positively identified in 1999 by Chandra as a bright X-ray point. Its spectrum is best fitted by a neutron star with a carbon atmosphere, which was the first time such an atmosphere had ever been inferred for any object. It also appears to be cooling unusually fast. The surface temperature fell from 2.12 million Kelvin in the year 2000 to 2.04 million by 2009, a decline of about 4% in a decade. The leading explanation is that the neutrons in its core have recently become superfluid, releasing a burst of neutrinos. That is a model, not a settled result, and quantum criticality and internal heating both remain in the literature as competitors. The remnant has one further trick, and it is the reason Cassiopeia A keeps producing results decades after it should have been exhausted. Webb's survey found dozens of those delayed reflections scattered around the remnant, ranging from a tenth of an arcsecond to a full arcminute in angular size. In 2024, the telescope observed one of them 3 separate times, on the 19th of August, the 16th of September, and the 30th of September. Because the reflecting surface moves outward through the dust cloud between observations, each visit lit up a different slice of the cloud. The result is effectively a three-dimensional scan of interstellar dust, resolving filaments down to about 400 astronomical units, less than 1/100th of a light year. The structures that came back look nothing like the diffuse fog interstellar dust is usually drawn as. They appear sculpted by magnetic fields, and the description the team reached for was muscle fiber, or the grain in a plank of wood. At the bottom right of Webb's near-infrared image sits a large, striated blob, the team nicknamed Baby Cassiopeia A. It is dust being warmed by the centuries-old flash, sitting about 170 light-years behind the remnant itself. It is not part of the remnant at all. It is the explosion's light, still traveling, still finding new material to illuminate, 3.5 centuries on. There is one more disagreement worth recording, because it is unusual for a space agency to state it so plainly in a press release. The near-infrared image, released on the 11th of December, 2023, shows no green loop whatsoever. The green monster simply is not there. The holes appear, faintly, as white and purple outlines, but the structure that dominates the mid-infrared view is absent from the near-infrared one. The European Space Agency's own release says that astronomers are investigating why that is. 2 instruments on the same telescope, pointed at the same object on the same nights, do not agree about what is in the frame. And the star that produced all of this is missing its partner. The standard explanation for how Cassiopeia A's progenitor lost its hydrogen envelope is that a companion star stripped it away, which is a common enough arrangement in massive binary systems. deep searches have ruled out any surviving companion of reasonable mass and age. Either the stripping happened some other way, or the companion is there and has evaded every attempt to find it. Even the interior is layered wrong. Work published in August 2026, combining Chandra with the newer X-ray observatory X-RISM, mapped the three-dimensional velocities of ion-emitting debris and found the southeastern material reaching 5,160 kilometers per second. That is faster than the silicon and sulfur. Inside a massive star, iron sits deepest, at the very core, with the lighter elements layered above it. When the star explodes, the outer layers should get out first and fastest. In Cassiopeia A, the material from the deepest layer is outrunning the material that was sitting on top of it. There is a reason astronomers keep coming back to this one object, beyond its own strangeness. The 2023 release framed Cassiopeia A explicitly as a test case for a much larger problem. Very young galaxies in the early universe are already full of dust, and exploding stars are the only plausible source of it, and no supernova anyone has ever observed makes enough. Cassiopeia A is where you go to find out how much dust a dying star actually produces. Which means the structure blocking the view is not merely inconvenient. It is standing in front of the answer to a question about the first billion years of cosmic history. The green monster had been visible for decades before anyone noticed it. Its brightest section already appears in Spitzer data from 2014, catalogued under a different name, and there are hints of it in observations from 1996. It has been sitting in the mid-infrared for at least 30 years, and it took an instrument sharp enough to resolve holes in it before anyone looked twice. That is the pattern this entire list follows. A better instrument arrives, resolves something that was previously a smear, and the smear turns out to have been hiding a contradiction. But the next object on this list is not 11,000 light-years away. It is close enough that a spacecraft is already on its way to it, and the thing nobody can explain about it is not what was found there. It is what was found, and then unfound, 13 years later. Number 9. The plumes of Europa that nobody can reproduce. Europa is the smallest of Jupiter's 4 large moons, and it is almost certainly the most interesting object in the solar system that is not a planet. Underneath a shell of water ice there is a global ocean of salt water, and NASA states that it may hold twice as much water as every ocean on Earth combined. The evidence for that ocean is not photographic. Nobody has ever seen it. The evidence is magnetic. Galileo, the spacecraft that orbited Jupiter from 1995 to 2003, measured a magnetic field around Europa that behaves the way an electrically conducting shell behaves when it sits inside a changing magnetic environment. Jupiter's field sweeps past Europa and induces a response, and the strength of that response tells you there is a conductor down there. Salty water is the obvious candidate. So the ocean was discovered the way you might discover a coin inside a sealed box, by noticing how the box reacts to a magnet. The heat that keeps it liquid comes from tides. Europa is caught in an orbital resonance with Io and Ganymede, which keeps its orbit slightly elliptical, and an elliptical orbit around a body as massive as Jupiter means the Moon is squeezed and released every 3.5 days. That flexing warms the interior. It is the same mechanism that makes Io the most volcanically active body in the solar system, applied to a world made mostly of water. How thick the ice is on top has been argued for 30 years, with estimates running from about 3 kilometers to over 30. The most recent direct constraint came from Juno's microwave radiometer, which observed Europa in 2022. Those results are consistent with a shell 29 kilometers thick, give or take 10, threaded with fractures and pores a few centimeters across, running hundreds of meters down. And the surface is broken. Chaos terrain, where the ice has fragmented and refrozen into a jumble, covers as much as 40% of the Moon. So the question that has consumed 2 decades of telescope time is easy to state and extremely hard to answer. Does that ocean ever get out? Because if it does, the consequences are enormous. A spacecraft would not need to land or drill through 30 kilometers of ice or do anything difficult at all. It could fly through the spray and taste an alien ocean directly. That is the entire prize, and it is why what happened next mattered so much. In November and December of 2012, Hubble's imaging spectrograph observed Europa in the far ultraviolet. Lorenz Roth, then at the Southwest Research Institute in San Antonio, and his colleagues reported statistically significant surpluses of hydrogen and oxygen emission above the Moon's southern hemisphere. The signal stayed in the same place for about 7 hours, and it was consistent with 2 plumes of water vapor reaching roughly 200 kilometers high. The paper was published in the journal Science on the 12th of December 2013 and announced at a large geophysics meeting in San Francisco. It was a beautiful result. And there was a detail in the same paper that should have been read more carefully than it was. The emission was absent in November 2012, a few weeks earlier. It was absent from Hubble images taken in 1999. It appeared once. It also appeared at the right time, which is what made it persuasive. Europa's orbit carries it closer to and further from Jupiter, and the tidal stress on the South Pole should peak when the Moon is furthest out. That is exactly where the detection fell. The physics agreed with the picture, and the picture was of a moon venting water when it gets stretched. So Roth's team went back to check. On the 22nd of January and the 2nd of February 2014, they deliberately scheduled Hubble to catch Europa at that same orbital position, the point where the plumes should have been strongest. They found nothing. No localized hydrogen emission, no localized oxygen emission, nothing above the limb at all. The paper they published carries one of the most self-critical titles in the field. Orbital position, it says, is not a sufficient condition for detecting Europa's water vapor aurora. Across 5 sets of Hubble ultraviolet observations, 1 showed the emission and 4 did not. A different team tried a different approach entirely. William Sparks at the Space Telescope Science Institute, with Kevin Hand at the Jet Propulsion Laboratory and Melissa McGrath at the SETI Institute, imaged Europa in silhouette. When the Moon passes across Jupiter's bright disk, anything sticking up off its limb should appear as a dark absorption feature against that background. It is the same principle as noticing steam rising off a kettle by looking at it against a window rather than against a wall. 10 transits were observed between December 2013 and March 2015. Published in September 2016, the result was that 3 of the 10 showed features that could implicate plume activity. 2 of those were at latitudes similar to Roth's. 1 was closer to the equator. The strongest, on the 26th of January 2014, showed dark spikes reaching about 220 kilometers and implied a mass of water almost exactly matching Roth's 2-plume model. What makes that paper unusual and worth honoring is how openly the authors doubted themselves in print. They wrote that they could not find any explanation that definitively accounted for the features, although there were reasons to be cautious. Then they listed the reasons. The January image used the smallest detector drift, which makes flaws in the detector's flat response more pronounced rather than less. In the March image, Europa sat closest to Jupiter's edge, where subtracting the background is hardest. The April image showed a suspicious bright rim on the opposite side from the dark one, which they said could indicate a problem in the data processing. and they wrote, pointedly, that Roth's almost simultaneous non-detections gave them pause and represented a cause for concern. That is a discovery paper, containing a section explaining why the discovery might not be real, written by the people making it. The technical demands of that silhouette method are worth appreciating, because they explain why the answer has been so hard to pin down. Sparks's observations recorded individual photons with a time resolution of 125 microseconds, typically collecting 40 to 50 million separate photon events per image. The filter they used has a known flaw. Roughly a third of the photons it lets through are at wavelengths longer than it is supposed to pass, and the authors noted that the actual size of that leak is very uncertain because it has never been calibrated on orbit. To model how the telescope smears a point of light, they used 31 separate observations of a globular cluster and then rejected those models as too diffuse to be useful. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. At the ultraviolet wavelengths involved, the telescope's resolution limit corresponds to about 38 kilometers on Europa's surface, from 4 astronomical units away. Everything in this dispute is happening at or near the edge of what the instrument can physically distinguish. The plume itself was always a stretch, theoretically. To reach 200 kilometers, the water would need to leave the surface at about 700 meters per second, from vents warmer than 230 Kelvin, on a moon whose surface sits near 100. For comparison, Enceladus, where the plumes are certain, ejects gas at 300 to 500 meters per second. And modeling work published in the year 2000 had predicted Europa plumes reaching only 1 to 25 kilometers, with about 100 as an extreme upper bound. Roth's detection was double the theoretical ceiling, which is either an important discovery or a warning, depending on how it turns out. The two sets of detections also disagree with each other in ways that are rarely mentioned. Sparks's 3 candidate events fall at orbital positions intermediate between the closest and furthest points from Jupiter, which led the authors to reject the tidal activity cycle that had made Roth's timing so persuasive. And they sit about 90 degrees further west in longitude than Roth's 2012 event. 2 teams, 2 methods, 2 sets of candidate plumes in different places at different points in the orbit. In 2018, the case appeared to firm up from an unexpected direction. Xianja Jia, Margaret Kivelson, Krishan Khurana, and William Kurth went back to Galileo's flyby of the 16th of December, 1997, which had passed below 400 kilometers. Reanalyzing the magnetometer and plasma wave data, they found a rotation in the magnetic field on a 1,000-kilometer scale, a drop of over 200 nanotesla in field strength, and intense localized plasma wave emission implying a brief spike in density. The interpretation was that Galileo had flown straight through a plume in 1997, and nobody had realized it for 21 years. That is a wonderful story. It is also, as of February 2026, contradicted by a different instrument on the same spacecraft during the same flyby. Analyzing Galileo's plasma subsystem data, Patterson and colleagues measured densities near closest approach of roughly 400 to 560 particles per cubic centimeter. The plume interpretation required around 2,100. Their paper's title states the conclusion without ornament, refuting an encounter with a cryovolcanic plume. Their reading is that Galileo passed through Europa's ionosphere, which is patchy and uneven, and not through anything erupting. There is a second Galileo plume claim from a later flyby, based on magnetic signatures and on depletions in energetic protons. Jia and colleagues published a formal comment arguing that one of those features was an artifact. The original authors published a reply the same year. That exchange was never resolved, and it sits in the literature exactly as it was left. One correlation from the Sparks work does still stand and remains genuinely interesting. One of their candidate plumes coincides, within the uncertainties, with the highest nighttime surface temperature ever measured on Europa, recorded by an instrument on Galileo. If that heat is coming up from a subsurface reservoir of water, they modeled its depth at about 1.8 to 2 kilometers, which would be a very long way above the ocean and a very long way below the surface. Whether it is reservoir heat, a thin window in the ice, or simply vapor that has settled around a vent and changed how the surface holds warmth, nobody can currently distinguish. The 2026 reanalysis was not purely subtractive either. In the process of removing the signal, it established something real and permanent. Europa is surrounded by a persistent envelope of hydrogen at roughly 1,000 Kelvin, present in every epoch examined. The measurement that took the plumes away found an atmosphere instead. And then, on the 18th of May 2026, came the result that reorganized this entire item. Roth, now at the Royal Institute of Technology in Stockholm, together with Kurt Rutherford at the Southwest Research Institute and their colleagues, reanalyzed 14 years of Hubble ultraviolet data. Every sunlit, non-transiting observation from 1999 and from 2012 through 2020. They built a forward model of every known source of that ultraviolet emission, including sunlight scattered by Europa's own thin envelope of hydrogen, subtracted it, and examined what was left over. Their finding was that no localized emission enhancements are detected in any of the observations, including, explicitly, the image previously interpreted as evidence of water aurora near Europa's south pole. Then they did the thing that makes the result airtight rather than merely contrary. They showed that if you adopt the old assumed position of Europa's disk on the detector and leave out the hydrogen envelope term, the original detection comes back at the same significance. They did not merely fail to find it. They identified the two specific choices that produce it. Rutherford's summary was that if Europa's placement was off, even just by a pixel or two, it could affect how the data gets interpreted. Roth's own statement is one of the cleanest sentences any scientist has ever said about their own famous result. The reanalysis, he said, took their original 99.9% confidence in the plume's existence and reduced it to less than 90%, and that is simply not enough evidence to support the certainty of the claims they made at the time. It is worth sitting with that for a moment. For 13 years, the sentence "we have seen water leaving Europa" appeared in textbooks, in documentaries, in mission proposals, and in the funding case for a spacecraft that has already launched. The reason it is no longer there is that the man who first wrote it went back, checked, and published the correction himself. He was careful to add that the plumes are not ruled out, only that the evidence for them is gone. Three things survive. The first is the one direct detection of the water molecule itself, which did not come from Hubble at all. Lucas Paganini, Geronimo Villanueva and colleagues used a spectrograph at the Keck Observatory in Hawaii to look for water directly and found it on exactly one of 17 observing dates spread across 15 months. The date was the 26th of April, 2016. The amount was 2,095 metric tons, plus or minus 658, at a release rate of about 2,360 kilograms per second. Paganini's own framing was careful in the same way Sparks's had been. The interesting thing about the work, he said, was not only the first direct detection of water above Europa, but also the lack of it within the limits of their method. The second is Sparks's silhouette features. They have never been retracted, never been independently reproduced, and the 2026 reanalysis deliberately excluded transiting observations, which means it does not touch them at all. The third is Webb's answer, which is worth reporting precisely because it is not a null result. On the 23rd of November, 2022, Webb's near-infrared spectrograph observed Europa. The paper that followed is titled "In Full, Endogenous Carbon Dioxide Ice Mixture on the Surface of Europa and No Detection of Plume Activity." The carbon dioxide is the important half. It is concentrated in a chaos terrain region called Terra Regio, and the ratio of carbon isotopes indicates it came from inside the Moon rather than being delivered from outside. That is genuine evidence that the ocean is chemically connected to the surface, which is most of what anybody wanted the Plumes for. And the Plume search found nothing. No water, no carbon monoxide, no methanol, no ethane, no methane. Villanueva's summary was appropriately narrow. "We only have one specific measurement done now," he said, "and at that particular moment, we didn't see the plume." For contrast, this is what an unambiguous plume looks like. Cassini's cameras imaged Saturn's small moon Enceladus in 2005 and found an enormous cloud of water vapor above 4 warm fractures near the South Pole, each about 135 kilometers long. Carolyn Porco's team went through 6.5 years of imaging and located 101 individual geysers. Then Cassini flew directly through the spray, sampled it, and found complex organic molecules in it. Nothing remotely comparable has ever been done at Europa, which is precisely why the question is still open after 20 years of trying. It will stay open for a while yet. Europa Clipper launched on the 14th of October 2024. It is the largest spacecraft NASA has ever built for a planetary mission, about 30 meters across with its solar arrays extended, and it will travel roughly 2.9 billion kilometers before arriving at Jupiter in April 2030. It has already used Mars for a gravity assist, passing 884 kilometers above the surface on the 1st of March 2025, and testing its radar and thermal imager on the way through. It is the first NASA mission ever dedicated to studying an ocean world beyond the Earth. From 2031, it will make 49 close passes of Europa, some as low as 25 kilometers above the ice. 3 of its 9 instruments bear directly on this question: a dust analyzer to catch grains thrown off the surface, a mass spectrometer sensitive enough to measure trace gases at parts per million, and an ultraviolet spectrograph that uses the same technique Hubble used from about 100 times closer. That is a moon where the question is whether we have seen something at all. The next item is stranger, because there is no doubt whatsoever that the object exists. It is bright enough to find with a backyard telescope, and the problem with it is that it keeps measuring older than the universe. Number 8. The star that measured older than the universe. There is a star in the constellation Libra, about 190 light-years away, bright enough at 7th magnitude that a modest backyard telescope will find it on any clear night. Its catalog designation is HD 140283. Its nickname is the Methuselah star, and it earned that name by returning an age older than the universe it lives in. It is a subgiant, which means it has finished burning hydrogen in its core and has begun to swell and cool on its way toward becoming a red giant. It is extremely poor in heavy elements. Its iron content is around 1/200th of the Sun's, which is the chemical signature of a star that formed before generations of exploding stars had time to enrich the galaxy with anything heavier than helium. And it is not a local resident. Its motion across the sky corresponds to 319 kilometers per second, and its motion toward us is another 169, giving a total speed relative to the Sun of 361 kilometers per second. That is roughly 1.3 million kilometers per hour. It is on a highly eccentric, backward orbit, diving down through the plane of the galaxy from the ancient halo and heading back out again. It belongs to the oldest structural component of the Milky Way, and it is passing through our neighborhood at speed, the way a comet passes through the inner solar system. It is also, thanks to interferometry with an array of telescopes in California, one of the few stars whose physical size has been measured rather than inferred. Its angular diameter is 0.325 milliarcseconds, which works out to a radius 2.17 times the Sun's. The story of this star begins long before anyone was trying to date it, and the beginning is worth telling because it is a good illustration of how slowly this field can move. In 1912, Walter Adams at Mount Wilson published on it as a high-velocity star with an anomalously early spectral type for its low luminosity. In plain terms, its spectrum looked like a much hotter star's spectrum, and nobody could explain why. The absorption lines that should have been strong were weak. That observation sat unexplained for 39 years. In 1951, Joseph Chamberlain and Lawrence Aller finally worked out what was happening. This star, along with one other, had a far lower heavy element content than the Sun. They were the first stars ever demonstrated spectroscopically to be metal poor. The weak lines had nothing to do with temperature. They were an absence. The elements that make those lines had not existed in sufficient quantity when this star condensed. So why does this particular star carry so much weight? Because of where it sits in the diagram astronomers use to classify stars. A subgiant occupies the one region where a star's true brightness is most sensitive to its age. Get the distance right, and you get the true brightness. Get the true brightness and the chemical composition right, and the models hand you an age. That is a much cleaner proposition than dating a globular cluster, where the answer depends on modeling thousands of stars whose distances and dust reddening are all tangled together. This star is bright, close, unobscured by dust, and chemically well characterized. It is the cleanest single-object clock in the sky, and that is exactly why the number it returned was so difficult to dismiss. In 2013, Howard Bond at Penn State and the Space Telescope Science Institute, with Edmund Nealon, Don Vandenberg, Gail Schaefer, and Diane Harmer, measured its distance to a precision nobody had managed before. They used the fine guidance sensors on the Hubble Space Telescope across 11 sets of observations recorded between 2003 and 2011. It is worth pausing on what those instruments are, because it is a genuinely elegant piece of improvisation. The fine guidance sensors are not cameras. They are the pointing system. They are what Hubble uses to lock onto guide stars and hold itself rigid while the science instruments expose. Astronomers turned the telescope's own steering mechanism into a distance measuring device and got a parallax with an error 1/5 the size of the previous best from a dedicated astrometry satellite. Feeding that distance into stellar models that included helium settling, revised nuclear reaction rates, and an enhanced oxygen abundance, they arrived at an age of 14.46 billion years. The universe, measured from the cosmic microwave background, is 13.8 billion years old. The star came out about 700 million years older than everything. Now the paper itself was far more careful than the headlines it generated, and the careful version is more interesting. Its title was Measured, a star in the solar neighborhood that formed shortly after the Big Bang. And the text stated explicitly that the quoted error included only the uncertainty and the parallax. Uncertainties in the star's chemical composition, and especially in its oxygen content, now contribute more to the age error than the distance does, which pushes the real total uncertainty out to about 800 million years in either direction. Their own conclusion was not that the star breaks cosmology. It was that within the errors, the age does not conflict with the age of the universe, but that the star must have formed very soon after the beginning. Oxygen matters here more than any other element, and the reason is technical but worth stating. In a star this metal-poor, oxygen dominates the opacity, meaning it controls how easily radiation escapes from the interior. Change how much oxygen you assume, and you change how the star's structure evolves, and therefore how old it has to be to look the way it looks. Raise the assumed oxygen, and the inferred age falls. What happened over the following 13 years is the actual story here, and it is stranger than the headline. In 2013, Bond and colleagues got 14.46 billion years. In 2014, Vandenberg and colleagues got 14.27. In 2015, Creevy and colleagues got 13.7, which was the first result fully compatible with the age of the universe. In 2018, Joyce and Chaboyer produced a range spanning 12.5 to 14.9. In 2021, Tang and Joyce, using a different stellar evolution code combined with the interferometric radius, got 12 billion years, plus or minus half a billion once modeling uncertainties were folded in. Then, in 2024, Guillaume and colleagues did something almost nobody does. They computed opacity tables specifically for this one star, built from three-dimensional models of its atmosphere, rather than using the general-purpose tables everyone else uses. With those tailored tables, they got 12.3 billion years. With an ordinary solar-scaled mixture and the same machinery, they got 14. Same star. Same code. Same team. 1.7 billion years apart, depending entirely on what you assume the star is made of. And there was a further problem they identified honestly. Tailoring the composition and lowering a parameter that describes how convection carries heat inside the star produce the same effect on the derived age. The two cannot currently be separated, and they found no independent physical evidence favoring the lower convection value. The scale of the tailoring in that 2024 study is worth appreciating. Their model grid ran from 0.66 to 1.02 solar masses in steps of 1/100th, with the initial helium abundance fixed at the primordial value produced in the first minutes after the Big Bang. They removed the pre-main sequence phase entirely from the calculation, because for a star this old, it can safely be excluded. And the composition disagreement they were probing comes down to a single number. Their tailored mixture gives an overall metal abundance of -1.82. The standard solar-scaled treatment uses -2.29. Half a dex apart, on the same star, and that gap drives most of the age disagreement in the entire literature. There is also a piece of physics that has to be included for the models to work at all, and which quietly shifts the answer. Heavy elements in a star like this settle downward under gravity over billions of years, which would strip the surface of metals far faster than we observe. To reproduce the star's actual surface chemistry, the models require turbulent mixing to fight that settling. The physics that lets the star match its own spectrum is the same physics that changes how old it comes out. And underneath all of it sits a systematic pattern that runs through every paper ever published on this object. Higher inferred masses correlate with younger ages. That is not a coincidence. It is a direct consequence of how stars burn. Which is precisely why an independent measurement of the mass was the missing piece for 13 years, and why one particular number from 2025 is the one to watch. Then came 2025, and a measurement that broke a 13-year deadlock in method. Every earlier age came from fitting the star's position on a brightness-temperature diagram to model tracks, which means every earlier age depended on an assumed mass. Mass is what sets how long a star burns, so if the mass is wrong, the age is wrong, and the two are almost impossible to disentangle from a photograph. Astroseismology gets around that. Stars ring. Sound waves bounce through their interiors and cause the surface to rise and fall by tiny amounts, and the frequencies of those oscillations depend directly on the star's internal structure and mass. The satellite TESS observed HD 140283 at 20-second cadence, and Lundqvist and colleagues extracted a rich spectrum of oscillations from the light curve, including the mixed modes that penetrate deepest. Their result was a mass of 0.75 solar masses, a radius of 2.078, and an age of 14.2 billion years, plus or minus 0.4. The paper describes that as in agreement with the upper limit set by the age of the universe within one standard deviation. Read that carefully, because the phrasing is doing a lot of work. The most physically constrained measurement ever made of this star, using an entirely independent technique that finally pinned down its mass, returned a number above the age of the universe and touches consistency only at the very edge of its error bar. The same analysis produced an unrelated surprise that may matter more in the long run. The frequency at which the star's oscillations peak came out at 611 microhertz, which is the highest ever measured for any star this poor in metals. Standard scaling relations predict 537. That is a 14% discrepancy in relations that are used to derive masses for tens of thousands of stars. If those relations drift at low metallicity, the drift propagates outward into a great deal of stellar astronomy. The oscillation measurements themselves are worth recording because they are extraordinarily delicate. The large spacing between consecutive frequencies came out at 39.468 microhertz, with a period spacing of 147 seconds. 6 radial oscillation modes were recovered, and all 3 independent extraction methods agreed on all 6, which is the kind of consistency that makes a result hard to argue with. Curiously, most of the quadrupolar modes were too faint to detect reliably. Only one was recovered, and it was excluded from the final modeling as insufficiently secure. There is one further wrinkle that has not been resolved. Gaia's revised parallax places the star very slightly further away than Hubble's fine guidance sensor measurement did. Further away means brighter, and brighter means more massive, and more massive means younger. The distance that started this entire argument is still being adjusted. It helps to picture what this object actually is, rather than what it represents. It is small, and it is dim, and it is falling. Formed out of gas that contained almost nothing except hydrogen and helium, in a galaxy that had not yet manufactured most of the elements a human body is built from. There was essentially no carbon in it. Almost no oxygen. Barely any iron. When this star condensed, the periodic table as we experience it did not yet exist in any useful abundance anywhere nearby. It has been falling through the Milky Way ever since, on a long backward loop that carries it out into the halo and back down through the disk. It is doing that now at 361 kilometers per second, which means that in the time it takes to say a sentence, it moves about the width of Great Britain. Everything around it in our sky is younger. The Sun is younger by 8 billion years. Every star visible to the naked eye tonight is younger. It is passing through a neighborhood that assembled long after it did, and it will keep going, and in a few 100,000 years, it will be gone from this part of the galaxy entirely. Bond and colleagues were explicit about why this star was worth so much effort in the first place. Its value, they wrote, was that it avoids the globular cluster problem entirely. You can date one star cleanly In a way, you simply cannot date a cluster of 100,000 of them. And there is a quiet irony in where that has ended up. HD 140283 is now the second most metal-poor object in the reference catalogue that other stellar measurements are calibrated against. A star that may be older than the universe is being used as a yardstick. It is also worth noting that the comparison has moved on both sides. The 2021 analysis anchored its conclusion to a universe age of 13.5 billion years, rather than 13.787. The star has been measured against slightly different universes in different papers, which is a small thing, and which matters when the entire question is a gap of a few 100 million years. It is also worth saying what this star is not. It is not the last survivor of a crisis that has otherwise been resolved without cost. In the mid-1990s, globular cluster ages were being derived at 14 to 16 billion years, in open conflict with the age of the universe, implied by the expansion rate estimates then in use. Astronomers were seriously discussing a universe younger than its own contents. The Hipparcos astrometry satellite broke that deadlock by showing globular clusters were further away, and therefore younger than believed. By 1998, the mean age of the oldest clusters had been revised to 11.5 billion years. The paradox dissolved without touching cosmology at all. HD 140283 is the one object that never fully came down. There is independent evidence that the early universe did make stars very fast, and it uses a completely different clock. In 2007, Anna Frebel dated a star called HE 1523-0901 by radioactive decay rather than by models. Using a very high-resolution spectrum from the Very Large Telescope, she measured uranium and thorium and combined 4 separate decay chronometers for a weighted age of 13.2 billion years. Uranium had been detected in only 2 other stars before that, and only one of those had given a usable age. That measurement does not depend on convection models or opacity tables at all. It depends on nuclear half-lives, which are not in dispute. So the honest position on the Methuselah star is not that it disproves cosmology. It is that after a century of observation, 8 independent age determinations, a dedicated Hubble campaign, bespoke atomic physics, and the first astroseismic analysis ever performed on it, the answer still ranges from 12 billion years to 14.5, and the newest and best constrained number sits on the wrong side of the line. That is one star that does not fit inside the universe. The next item on this list is a discrepancy that covers the entire space between galaxies, and it was found by counting shadows. Number 7. The missing ultraviolet light. In 2014, Juna Kollmeier at the Carnegie Observatories, working with David Weinberg, Benjamin Oppenheimer, and Francesco Hart, published a short paper with a title that is also its own summary: The Photon Underproduction Crisis. The finding was that the nearby universe contains roughly 5 times more ionizing ultraviolet light than every known source in it can account for. Not 5% more. 5 times more. And the sources in question are not obscure. They are quasars and star-forming galaxies, which is to say, the 2 brightest categories of object that exist. Carnegie announced the result on the 8th of July 2014, under the headline that Cosmic Accounting Reveals a Missing Light Crisis. That framing turned out to be exactly right, and not in the way the press release intended. This was an accounting problem. Somebody had added up all the light sources in the nearby universe, added up all the light the universe visibly contained, and the 2 columns did not match. The numbers behind that headline were sharper still. The simulations underpredicted how much light was being absorbed by intergalactic hydrogen by at least a factor of 2, which the paper describes as a 10 sigma discrepancy with observations. 10 sigma is not a marginal result. And the predicted distribution of hydrogen clouds was systematically elevated compared to what was actually seen, across nearly 2 decades in density. Put the two together, and to make theory match observation, more than 80% of the hydrogen ionizing photons in the local universe would have to be coming from somewhere nobody had identified. It is worth being precise about what a factor of 5 means in this context, because the number is easy to hear and hard to feel. If you stood in a room lit by a single lamp and measured the brightness, and then measured how much light every visible source in the room could possibly be producing, and found that the room was 5 times brighter than the lamp could account for, you would not conclude that you had made a rounding error. You would start looking for a window. The intergalactic medium had no window that anybody could find, and it had been searched thoroughly, because quasars and star-forming galaxies are the most conspicuous objects in the sky, and their numbers had been counted for decades. To understand how anyone could possibly measure that, you have to understand that this is done by weighing shadows. The space between galaxies is not empty. It is mostly hydrogen, thinly spread, and it is by an enormous margin the most abundant material in the universe. Ultraviolet photons above a specific energy strip, electrons off hydrogen atoms. Left alone, those atoms recombine, catching electrons again. The balance between those two processes, ionization and recombination, sets how much neutral hydrogen survives at any moment, and therefore how transparent intergalactic space is. Now, neutral hydrogen absorbs light at one particular wavelength very strongly. So when light from a distant quasar crosses billions of light-years on its way to us, every cloud of neutral hydrogen it passes through stamps an absorption line into the spectrum. And because the universe is expanding, each of those clouds is receding at a different rate depending on its distance, which shifts each absorption line to a slightly different wavelength. The result is a picket fence. A single quasar spectrum arrives at Earth, carrying dozens or hundreds of narrow dark lines, and each line is a separate cloud of hydrogen, at a separate distance, along one line of sight stretching across a substantial fraction of the observable universe. Astronomers call it the Lyman Alpha Forest, and it is one of the most information-dense objects in observational cosmology. One spectrum, hundreds of measurements, a core sample drilled through the universe. Count the trees in that forest, and you have weighed the ultraviolet light that thinned it. If the light is intense, most of the hydrogen is ionized, absorption is weak, and the forest is sparse. If the light is weak, neutral hydrogen survives, and the forest is thick. There is one reason this particular measurement required Hubble, and it is a detail that usually gets skipped. At great distances, the expansion of the universe stretches that hydrogen absorption line out of the ultraviolet and into visible wavelengths, where any large ground-based telescope can see it. But in the nearby universe, there has been no such stretching. The line stays in the ultraviolet, and Earth's atmosphere blocks ultraviolet completely. The nearby Lyman Alpha Forest is simply invisible from the ground. It does not matter how large your telescope is, or how good your sight is. The instrument that opened it was the Cosmic Origins spectrograph, installed on Hubble by hand during the final servicing mission in 2009. That is worth stating plainly. The measurement that produced this crisis was made by a device carried up in a shuttle payload bay and bolted into the telescope by people in pressure suits, on the last occasion any human being ever touched Hubble. The observational backbone came from a survey by Charles Danforth and colleagues covering 82 ultraviolet bright active galaxies, cataloging 5,138 individual absorption lines across hydrogen and 25 different metal ions, grouped into 2,611 distinct systems. The survey also implied something worth holding on to. Those hydrogen clouds account for 25 to 30% of the entire inventory of ordinary matter in the universe. This is not a minor component. A quarter of all the normal matter there is sits in that forest. Here is the structural oddity that turned a discrepancy into a crisis. The mismatch exists only nearby. The same simulations, using the same physics and the same assumptions, reproduce the distant early Lyman alpha forest without any adjustment whatsoever. Look far away, and therefore far back in time, and the accounting balances perfectly. Look at the last several billion years, and it does not. The problem is not with the beginning of the universe. It is with the recent past. Oppenheimer's framing captured why that was so uncomfortable. The simulations, he said, fit the data beautifully in the early universe, and they fit the local data beautifully if we are allowed to assume this extra light is really there. It is possible the simulations do not reflect reality, which by itself would be a surprise, because intergalactic hydrogen is the component of the universe that we think we understand the best. That sentence is the heart of this item, and it is worth sitting with. Cosmology has plenty of things it does not understand. Dark matter has never been detected directly. Dark energy has no accepted physical explanation. The behavior of matter falling into a black hole is not fully described by any theory anyone trusts. All of that is known and expected. But hydrogen in empty space is supposed to be the easy part. It is one proton and one electron, in a vacuum, obeying atomic physics that has been understood since the 1920s, illuminated by sources we can see and count. That was the part that stopped adding up. The paper's own conclusion was that either the conventional sources of ionizing photons must be significantly elevated relative to observational estimates, or our theoretical understanding of the low redshift universe is in need of substantial revision. And it noted that none of the available resolutions alone appeared entirely satisfactory. Then it raised the possibility that made the paper famous. That the discrepancy is probing exotic sources of ionizing photons or heating mechanisms operating far above theoretical expectations. Specifically, decaying dark matter. The paper noted that producing the required energy would need the decay of only about 1/10,000,000th of the dark matter over the entire age of the universe, which is a small enough fraction to be hard to rule out. Kohlmeier's own line has been quoted ever since. "You know it is a crisis," she said, "when you start seriously talking about decaying dark matter." What happened next is one of the better illustrations of how a scientific crisis actually gets dismantled, which is almost never by a single dramatic discovery. The first correction was that the discrepancy had been overstated. In 2015, Michael Shull, Evan Maloney, Charles Danforth, and Gregory Tilton reanalyzed the same Hubble data using different simulations and concluded the required correction was closer to a factor of 2 or 3 than 5. They identified the dominant uncertainty as the fraction of ionizing photons that escape from star-forming galaxies rather than being reabsorbed inside them, and described that quantity as highly directional and difficult to constrain statistically. A galaxy does not leak ultraviolet light evenly in all directions. It leaks through whatever channels the gas happens to have opened, and whether you see the leak depends on whether you are standing in front of one. Shull's team did something worth noting as a check on themselves. Rather than relying on the hydrogen alone, they cross-checked their recommended ionization rate against the observed ratios of different metal ions in the same intergalactic gas, carbon in 2 different ionization states, silicon in two different ionization states. Different elements, different ionization energies, same underlying radiation field. If your assumed light level is wrong, those ratios come out wrong too. Theirs came out consistent. The second correction was that the source counts were wrong. Also in 2015, Vikram Khaire and Raghunathan Srianand showed that the quasar contribution to the ionizing background had been underestimated by a factor of about 2. And they showed that if only 4% of ultraviolet photons escape from star-forming galaxies, that is enough to supply the missing light. Their verdict was blunt. The crisis, they wrote, is not as severe as it was perceived, and there seems no need to look for alternative explanations such as hidden quasars or decaying dark matter particles. The third correction was that the simulations were missing physics, and this one is the most interesting of the four. In 2017, Alex Gurvich, Blakesley Burkhart, and Simeon Bird redid the comparison using a simulation that includes feedback from active galactic nuclei, that is, the enormous outflows driven by supermassive black holes as they accrete. The original work had not included it. And it turns out that heating the intergalactic gas mimics the effect of adding more light, because hotter gas recombines less efficiently, and gas that recombines less efficiently stays ionized and stops absorbing. You do not need extra photons. You need warmer hydrogen. With strong enough feedback, the required increase in light drops from 5 times to about 1.8. That study was careful about alternatives, which is what makes its conclusion usable. The team explicitly tested and ruled out supernova feedback, the technique used to fit the absorption lines and the finite resolution of the simulation itself, as significant influences on the result. Black hole heating was the only lever that mattered. And there is a useful diagnostic buried in the comparison. When the same group ran the analysis on a sibling simulation that uses different quenching physics but is otherwise similar, that simulation matched the observations less well. Which means the nearby forest genuinely can discriminate between competing models of how black holes affect their surroundings, a capability nobody had been looking for, and which fell out of trying to solve a different problem. Other independent modeling landed in between the extremes. Work published in 2017 using a purpose-built line-fitting routine found a hydrogen ionization rate at low redshift about 1.77 times the old reference value. Not 5 times, not 1, but somewhere in the middle, which is roughly where the field has settled. And the 2020 background model that helped close the gap produces an optical depth to reionization matching the cosmic microwave background measurement, with reionization ending around redshift 7.8. It is internally consistent with the early universe in a way its predecessor was not. The fourth correction was that the reference model everyone was comparing against was simply out of date. 3 modern models of the ultraviolet background superseded it between 2019 and 2020, incorporating updated galaxy and quasar counts, better stellar spectra, including the effects of binary stars, and improved measurements of how opaque intergalactic space actually is. The cleanest accounting arrived in 2020 from Jacob Christiansen, Romil Dave and colleagues. Without black hole jet feedback, they confirmed the crisis exactly. The required ionizing rate had to be raised by a factor of 6. Turning the jets on lowered the discrepancy to about 2.5. Adding the updated background model, in their own words, mostly resolves it. The mechanism they describe is startling in scale. Jet feedback lowers the fraction of ordinary matter sitting in the diffuse intergalactic medium from 39% to 16%, while raising the fraction in a hotter phase from 30% to 70%. Over billions of years, black holes have quietly cooked most of the gas between galaxies. The forest thinned, not because more light arrived, but because the trees were heated until they stopped absorbing. So why is this on a list of things nobody can explain? Because mostly resolves is not resolved, and because the residual is still being used to constrain new physics. No paper declares the problem closed. The literature uses conditional language throughout. Can resolve, mostly resolves, plausible solution. A factor of 5 became a factor of 1 to 2.5 through a stack of 4 separate moderate corrections, no one of which explains the whole thing. And the last of those corrections cannot be independently checked, because there is no independent measurement of how much gas actually sits in the diffuse intergalactic medium. That number is one of the things the forest is used to determine, which produces a genuine circularity, and the field says so openly. Black hole feedback strength and ultraviolet background intensity trade off against each other in fitting the same data. Turn one up, turn the other down, and the fit is equally good. So the nearby Lyman Alpha forest cannot currently constrain either quantity independently, and multiple analyses state plainly that a clear method to disentangle black hole feedback from other sources of heating remains elusive. There is also a residual that has not gone away. Comparisons of simulated and measured absorption at low redshift still find the simulations running about a factor of 1.5 below the measurements on average, and at least one thorough investigation reported that the cause could not be identified. And the correction that fixed the low-density end of the distribution broke the high-density end. The same simulation that finally matched the small clouds produces too few of the large ones. And the exotic option never entirely left the room. A paper in Physical Review Letters in 2022 found that reconciling the simulations with observations requires about 1/10 of an electron volt of heating per particle in intergalactic space, and identified the conversion of an ultralight dark matter candidate into low-frequency photons as a viable source of that heat. The mainstream explanation for the residual heating is black hole jets. But the residual is real enough that physicists are still using it to set limits on the properties of dark matter. Separate work has now treated the leftover heating requirement as a physics constraint in its own right, setting limits on non-standard heating and turbulence in intergalactic space. The quantity that began as a missing light problem became a black hole feedback problem, is now abound on exotic physics. It has changed category 3 times in 12 years without ever being fully explained. The most satisfying part of this story is the inversion at the end of it. The nearby Lyman Alpha forest is now routinely used as a calibration tool for black hole feedback models in cosmological simulations. The measurement that once looked like evidence of missing light has become the standard instrument for measuring how much black holes have heated the universe. The crisis did not get solved so much as repurposed. All 4 items so far have been about things that are missing or unaccounted for or measured wrong. The next item is the opposite problem. It is about something that should not be there at all, and there are 42 of them in the nearest place to Earth where stars are being born. Number 6. The paired planets of Orion. The Orion Nebula is the nearest place to Earth where massive stars are being born, and it is close enough that you can see it without any equipment at all. On a clear winter night, the middle star in Orion's sword is not a star. It is a cloud, 1,350 light-years away, in which several thousand stars are currently condensing out of gas. Radio interferometry gives a distance to the Orion Nebula cluster of 414 parsecs, plus or minus 7. At its heart sits the trapezium cluster, named for the 4 bright stars at its center, and the trapezium is extraordinarily young. Published ages run from about 300,000 years for the tight core to around 1 million, with the broader cluster often quoted at 3 million. Against the 8 billion years of the region of the galaxy it sits in, that is essentially the present moment. Youth is the entire reason anyone looks there. Objects below the mass of a small star are intrinsically faint because they have no fusion running inside them to keep them lit. But while they are young, they are still hot from the process that made them, and that residual heat glows in the infrared. A nearby, very young cluster is the only realistic place in the sky to detect free-floating objects below 13 Jupiter masses. That figure, 13, is not arbitrary. It is the mass below which not even deuterium will fuse. Deuterium is the heaviest and most easily ignited isotope of hydrogen, and it is the last fuel available to an object that cannot manage ordinary hydrogen fusion. Below 13 Jupiter masses, nothing burns at all. The object simply cools for the rest of time. That is the line astronomers use to separate a planetary mass object from a brown dwarf. The observations that produced this item were taken with Webb's near-infrared camera in September and October of 2022, under a guaranteed time program led by Mark Makorian of the European Space Agency. The images were taken in 12 separate filters from 1 to 5 microns, covering a mosaic about 11 arc-minutes by 7.5, roughly 1.25 parsecs by 9/10 of a parsec of the nebula. The resolution is the part that matters. The mosaic is diffraction limited at every wavelength, with a maximum spatial resolution of 63 milliarcseconds at 2 microns. At Orion's distance, that corresponds to about 25 astronomical units, which means Webb can resolve structures the size of Neptune's orbit at a distance of 1,300 light-years. Nothing had ever been able to do that before, and it is the whole reason this result exists. 2 papers appeared in October 2023 by Samuel Pearson and Mark Makorian. The headline count was 540 planetary mass candidates, with masses reaching down to 0.6 Jupiter masses, and with no sharp cutoff at the bottom of the distribution. That in itself was interesting. Star formation was expected to have a flaw, and this suggested it either does not have one, or the flaw is much lower than anybody had drawn it. But roughly 9% of those objects were in wide binaries. The follow-up literature standardizes on 40 binary systems plus 2 triples, which makes 42 multiple systems and 86 individual objects. Component masses span 0.6 to about 14 Jupiter masses. The separations between the pairs run from 28 to 384 astronomical units. To put that in familiar terms, the tightest pair sits about as far apart as Neptune is from the Sun, and the widest is roughly 10 times the Sun to Pluto distance. Orbital periods are estimated at 20,000 to 80,000 years. It is the combination that is anomalous, not either property on its own. Substellar binaries are known and studied, and typical ones have separations below 10 astronomical units, tight, tidally bound systems. Free-floating planetary mass objects are also known, in very large numbers. What has no precedent is objects at the very bottom of the mass range, bound to each other at separations that would be considered wide even for a pair of stars, with nothing else nearby. And none of them is associated with a star. They are free-floating, in pairs, in the dark. They were named JWMBOs, for Jupiter Mass Binary Objects. The reason they became one of the most argued about results of Webb's early years is that nothing in astrophysics makes them. The problem is two-sided, and each side eliminates the solution to the other. Route 1 is that they formed the way stars form. A cloud of gas collapses under its own gravity, fragments into pieces, and each piece contracts into an object. That mechanism has a flaw. The smallest fragment such a collapse can produce is generally put at 3 to 5 Jupiter masses, set by the physics of how efficiently a small clump can radiate away the heat of its own compression. Below that, the clump warms up faster than it can cool, and the collapse stalls. Most of the jumbo components sit below that floor. An object at 0.6 Jupiter masses should not be able to form this way at all. Route 2 is that they formed as planets, in orbit around stars, and were later thrown out. That part is entirely uncontroversial. Young planetary systems in crowded clusters are dynamically violent, and planets get ejected regularly. Simulations produce ejections in large numbers, and free-floating planets are known to exist in enormous quantities. The difficulty is the pairing. Ejection is a violent, near-instantaneous event, and a pair of objects bound to each other at 100 astronomical units or more is extraordinarily fragile. The gravitational bond holding two Jupiter mass objects together at that separation is weak. Whatever encounter is energetic enough to strip a planet away from a star should be far more than energetic enough to strip two planets away from each other. The pair should not survive the event that created it. Pearson and Mercurian wrote it carefully, how pairs of young planets can be ejected simultaneously and remain bound, albeit weakly at relatively wide separations, remains quite unclear. Pearson's public framing was blunter. There is something wrong, he said, with either our understanding of planet formation, or star formation, or both. It is worth trying to picture one of these places, because the numbers do not convey what they describe. You are standing on a world several times the mass of Jupiter, which means it has no surface in the ordinary sense. But suppose you could stand somewhere in its upper atmosphere. There is no sun. There has never been a sun. This object has never had a day, and it never will. The nearest significant light is the trapezium, 4 hot young stars burning across the nebula, close enough to be brilliant points, but far too distant to warm anything. Around them, the gas of the nebula glows faintly in every direction, so the sky is never fully black. It is the color of something being lit from inside. The only substantial thing in that sky is the other one. A second world, essentially identical, hanging there. If the pair sits at the close end of the observed range, it would be a distinct disk, noticeably larger than the Moon appears from Earth. At the wide end, it is a bright point and nothing more. Either way, it barely moves. A full orbit takes somewhere between 20,000 and 80,000 years, which means that over the entire span of recorded human history, from the first cities to now, these two objects would have completed something like 1/10 of one circuit around each other. Whatever heat there is comes from inside, left over from formation, and it is leaking away. Both objects are cooling and will continue cooling, and nothing will ever arrive to stop that. In a few 100 million years, they will be dark, and they will still be orbiting. There is one of these objects that answered back, and the story of it is a good illustration of how strange the whole business is. In 2024, Luis Rodriguez and colleagues searched the Very Large Array archive for radio counterparts to all 42 GUMBOs. They found exactly one. The object designated JWST was detected at 2 radio frequencies in 3 separate epochs spanning a decade, 2012, 2018, and 2022, with a flux holding steady at about 50 microjanskis over days and over years. The odds of a chance positional coincidence with any of the 42 are about 1 in 8,000. JWST 24 is the extreme member of the sample. It has the largest total mass at 23 Jupiter masses split evenly between 2 components, and the tightest separation at 28 astronomical units. The radio source is marginally resolved along the same east-west axis as the Webb binary, which implies emission coming from both components rather than one. And its radioluminosity is orders of magnitude above what quiescent ultra-cool dwarfs produce. Nobody has identified the emission mechanism. The measured spectral index is too uncertain to pin it down, though it does rule out simple thermal emission and pulsar-like emission. No circular polarization was detected at any epoch, which removes the most obvious remaining candidate, because circular polarization is the signature of the process that generates radio aurorae on cool dwarfs. The team searched more than the radio archive. They also went through 7 separate ALMA datasets, looking for millimeter wavelength emission from cold dust around any of the 42 objects, and found nothing at all, down to a detection limit of 750 microjanskis per beam. If these objects have disks around them, the disks are below that threshold. 50 microjanskis, incidentally, is a genuinely tiny signal, and the way its steadiness was established is worth noting. Across 5 separate observing sessions in 2012, the measured flux densities were 52.9, 39.7, 55, 44.9 and 40.5 microjanskis, all consistent with about 45. That scatter is what established the source is steady rather than flaring, which in turn rules out the burst-type emission that cool dwarfs normally produce. There was a precedent that made the detection interpretable at all. The first radio detection at centimeter wavelengths of any single planetary mass object was made in 2018. Cool dwarfs are known to produce 2 distinct kinds of radio emission: bursts from an auroral process and steady emission now understood to come from radiation belts of the kind Jupiter has. Neither cleanly fits what JWST 24 is doing. Then, the same object produced a flat contradiction. Ground-based spectroscopy from 2004 had classified that same source as a single star of spectral type M5.5, with a mass around 52 Jupiter masses. Webb photometry says it is 2 objects of 11.5 Jupiter masses each, 28 astronomical units apart. Both cannot be right. The object has a 25-year observational history under 3 different identities in 3 different catalogues, and the astronomers involved were, for most of that time, unaware they were looking at the same thing. The most serious challenge to the entire result came from Kevin Luhman at Penn State, and it is the reason this item sits at number 6 rather than higher. In 2024, Luhman reanalyzed the same Webb images using color-color diagrams, a standard technique that compares brightness across multiple filters to separate genuinely cool nearby objects from distant reddened ones. He identified more than 200 brown dwarf candidates in the cluster. And his key finding was that most of the objects previously identified as Jupiter mass binary objects are absent from his list. Their colors, he wrote, indicate reddened background sources rather than young brown dwarfs. Or their photometry is inadequate for assessing their nature at all because of very low signal-to-noise or detection in only a few bands. The distinction he is drawing is the classic trap of infrared astronomy. A cool object nearby and a hot object far away behind a great deal of dust can look very similar. Both are red. Telling them apart from photometry alone is genuinely difficult, and getting it wrong turns a distant galaxy into a nearby planet. In 2025, he closed the loop with spectroscopy, which settles the question in a way photometry cannot. Analyzing archival Webb spectra of 200 sources toward the cluster, he classified 53 as likely members, 24 of them brown dwarfs. 7 of those spectroscopic targets had previously been identified as JWSTs. All 7 turned out to be background sources. He went further, stating that only a few jumbo components have brown dwarf colors at all, and none of those form pairs with unusually wide separations or low masses relative to known binary brown dwarfs. So the honest position is this: 7 of 42 have been tested with spectroscopy. All 7 failed. The other 35 have not been tested. The debate has moved decisively toward Luhmann's reading without being settled, because settling it requires spectra of the remaining 35, and that is a substantial amount of telescope time on objects that may turn out not to exist. The images themselves became public quickly and widely. The wide-field mosaic was released through the European Space Agency's sky browsing application in early October 2023, and NASA featured the Orion image as its picture of the day on the 10th of that month. Millions of people looked at that mosaic. The paper announcing what was in it is only 24 pages long with 4 figures, which is remarkably compact for a result of this profile, and it reads like a team that knew exactly how contested the claim would be. Follow-up work is ongoing. Webb carried out spectroscopy of free-floating planetary mass objects and their disks between August and October 2024, covering 1 to 13 microns across 8 targets, and a dedicated spectroscopic survey of the Orion Nebula cluster remains in progress. The membership question, which of these objects actually belongs to the cluster and which is a distant galaxy seen through it, is the question those programs exist to answer. It is also worth saying what would settle this, because it is unusually concrete. Spectroscopy of the remaining 35 candidate pairs would end the argument in either direction within a single observing cycle. There is no theoretical obstacle and no missing technology. The reason it has not happened is simply that telescope time is allocated competitively, and a program to check whether 35 faint objects are real is a harder proposal to write than one that promises a discovery. There is a second, independent line of attack that does not depend on whether the objects are real at all. In 2025, a team led by Richard Parker placed populations of planet-planet binaries into simulations of dense star-forming regions and asked whether they survive. Between 50 and 90% are destroyed within a few million years. And wider binaries are preferentially destroyed at higher densities, which means that if Orion was denser in the past than it is now, and it very likely was, then the separations we observe today cannot be the separations they were born with. Many more must have formed than we now see, and their original distribution must have looked different from the one Webb measured. 3 formation models have been proposed, and none is confirmed. The first is ejection following a close flyby between 2 sun-like stars. The second, published in Nature Astronomy in April 2024, involves direct simulations showing that close stellar encounters can occasionally eject pairs of giant planets that remain bound to each other, rare but not impossible. The third is photoerosion, in which the ultraviolet radiation from the trapezium's massive stars erodes collapsing cores from the outside, whittling them down below the fragmentation floor. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. There is one more measurement that makes the problem worse rather than better, and it is the most quietly damaging fact in this entire item. Radio astrometry across a decade limits JWST 24's velocity across the sky to about 6 kilometers per second. That matters because simulations predict that planets ejected by strong stellar encounters move roughly 3 times faster than the cluster's stars, and Orion's stars have a velocity spread of only 2 to 3 kilometers per second. An ejected object should be moving noticeably faster than its surroundings. This one is not. It is drifting with the cluster. The paper's own conclusion is that this favors an origin similar to that of stars, from a stationary contracting core, which is precisely the route the object is too light to have taken. For context, isolated free-floating planets are not a problem at all. They are detectable in bulk only through gravitational lensing, by catching the momentary brightening when an unseen mass drifts in front of a background star. A 9-year analysis of one such survey, led by Takahiro Sumi, was announced in July 2023 and produced an estimate that co-author David Bennett summarized as 20 times more rogue planets than stars, trillions of worlds wandering alone in this galaxy. It was the first estimate sensitive to planets less massive than Earth, and it implies the Nancy Grace Roman Space Telescope could detect roughly 400 Earth-mass rogue worlds against a prior expectation of about 50. None of that troubles anybody. Isolated rogue planets fit comfortably inside known physics. It is specifically the pairs that nothing produces. Those objects may or may not be there. The next two items are about things that certainly are there and that are missing something they are supposed to have. Number 5. The galaxies with no dark matter. This story begins with an instrument that barely qualifies as a telescope. The Dragonfly Telephoto Array, designed by Roberto Abraham at the University of Toronto and Peter van Dokkum at Yale, is built out of commercial camera lenses. Specifically, Canon 400mm telephoto lenses, the kind sports photographers use. It was commissioned in 2013 with 3 of them and expanded to 48, arranged in 2 clusters of 24, mounted together and pointed at the same patch of sky. The combination gives an optical system equivalent to a 1-meter telescope at an extraordinarily fast focal ratio, covering roughly 6 square degrees at once. The reason for that design is specific, and it is a genuinely clever piece of reasoning. These particular lenses use nano-fabricated anti-reflection coatings, which give them exceptionally low internal scatter. And internal scatter is the precise enemy of low surface brightness imaging. When you are trying to photograph something extremely faint and diffuse, the thing that ruins the image is not the sky. It is light from bright stars in the field, bouncing around inside your own optics and spreading a haze across everything. Which means that for this one particular task, a very good camera lens outperforms a very good telescope. Astronomers had spent a century building larger and larger mirrors, and there was an entire category of object that those mirrors could not see, because the object was fainter than the glow their own optics produced. In 2015, the array found 47 galaxies in the Coma cluster that are roughly the size of the Milky Way and contain about 1,000 times fewer stars. Follow-up work estimated there were around 1,000 such objects in that cluster alone. The class acquired a name from then on: ultra-diffuse galaxies. Objects that had been sitting in one of the most studied regions of sky for the entire history of extragalactic astronomy, invisible because they were spread too thin. The same instrument, incidentally, found the exact opposite object. Dragonfly 44, studied by the same team, is an ultra-diffuse galaxy with a high stellar velocity spread and roughly 100 globular clusters, and it appears to be about 99.9% dark matter. One array of camera lenses found both extremes of the same class of galaxy, one with essentially none, one with almost nothing else. Whatever process makes ultra-diffuse galaxies is capable of producing objects at both ends of the range, and nobody can currently say why any given one lands where it does. The array has kept growing. Canon announced in November 2021 that it would supply 120 additional lenses, with coverage describing a target configuration of 168, light-gathering power equivalent to a 1.8-meter refractor with a focal length of 40 centimeters. The team is now building a successor instrument and using it to search for gas left over from the original collision. That search is ongoing and has not produced a detection. On the 28th of March 2018, Van Dokkum and colleagues published a paper in Nature titled, simply, "A Galaxy Lacking Dark Matter." The object is catalogued as NGC 1052-DF2. It was identified with Dragonfly and then observed with Hubble, with Gemini, and with the 10-meter Keck telescope. Hubble placed it at about 65 million light-years. It is larger than the Milky Way, and it contains roughly 250 times fewer stars. Van Dokkum's description of it has been quoted ever since, and it is accurate rather than poetic. "A gigantic blob," he said, "so sparse that you see the galaxies behind it. Literally, a see-through galaxy." The measurement that made it famous did not come from the starlight. It came from 10 unusually bright, compact objects orbiting the galaxy, identified as globular clusters. The logic is the same logic that has underpinned dark matter astronomy since the 1930s. Measure how fast things orbit, and you have measured how much mass is pulling on them. If the orbital speeds are higher than the visible material can account for, there is something else there. That comparison is how dark matter was discovered, and it has been repeated for essentially every galaxy ever studied, and the answer is always the same. There is far more mass than there is light. Here, the 10 clusters gave a velocity spread of 8.5 kilometers per second, with a 90% confidence upper bound below 10.5. Against a stellar mass of roughly 200 million suns, the total mass came out essentially equal to the stellar mass. Nothing extra. The European Space Agency's release stated the galaxy contains at least 400 times less dark matter than astronomers predict for a galaxy of its mass, and possibly none at all. Objections arrived immediately, and they were fair. 10 traces is a small number, and with a small number, the answer depends heavily on how you model the system. So Van Dokkum's team went back with a completely different method. Rather than tracking discrete clusters, they took an integrated spectrum of the galaxy's own diffuse starlight, using an instrument at Keck sensitive enough to measure the broadening of absorption lines in light that faint. That gives the velocity spread of the stars themselves, not of 10 objects orbiting outside them. The answer was 8.4 kilometers per second, no evidence of rotation, and a systemic velocity matching the globular clusters almost exactly. Two entirely different traces, two entirely different techniques, same result. A second object in the same field, DF4, was reported the following year. 7 globular clusters gave an intrinsic velocity spread of about 4 kilometers per second. And those clusters carried an oddity of their own that has never been explained either. On average, they are about 4 times brighter and twice as large as globular clusters are supposed to be. The globular clusters carry an unexplained anomaly of their own that tends to get lost behind the headline. DF2's cluster luminosity function peaks at least a full magnitude brighter than it should for a galaxy at 20 megaparsecs. Globular cluster brightnesses follow a well-behaved distribution across the observed universe, which is why they are used as distance indicators in the first place. These do not follow it. And there is a revealing wrinkle. If you take a distance derived from the internal motions of the clusters themselves, rather than from any external method, about 16 megaparsecs, the cluster mass distribution comes out comparable to the Milky Way's, and the anomaly largely dissolves. Which is a neat illustration of why the distance fight matters so much. At one distance, the clusters are impossible, and the galaxy has no dark matter. At another, the clusters are ordinary, and the picture softens. Both readings are currently defensible from the published measurements. Both galaxies' cluster populations have also been reported to show signs of rotation. If that rotation is real, it changes the implied total mass, because rotation contributes to the dynamics in a way that a simple velocity spread does not capture. Now, everything about this result hinges on distance, and this is where it becomes genuinely unresolved rather than merely surprising. Distance sets everything. It sets how large the galaxy is, how luminous, how much stellar mass it contains, and how bright its globular clusters really are. Push the galaxy closer, and it stops being a Milky Way-sized object with no dark matter and becomes an ordinary small dwarf galaxy whose clusters fall on completely normal relations. The entire result lives or dies on one number, and that number has been fought over for 7 years. Ignacio Trujillo and colleagues, in 2019, applied 5 separate redshift-independent methods and derived about 13 megaparsecs, which is 42 million light-years, considerably closer. Van Dokkum's team answered with 40 orbits of Hubble time, which is an unusually large allocation for a single faint dwarf galaxy and a direct measure of how contested this had become. Using the tip of the red giant branch, a technique that relies on the fact that red giant stars have a sharply defined maximum brightness, making them a standard candle, they measured 22.1 megaparsecs, later revised to 21.7 after an image alignment error was corrected. 2 independent measurements using surface brightness fluctuations gave 18.7 and 20.4. And then, in June 2026, 2 new measurements arrived. Hubble surface brightness fluctuations gave 17.7 megaparsecs. And new Webb observations gave a tip of the red giant branch distance of 17.6, plus or minus 0.6. Read those last 2 numbers against the earlier one carefully. The Hubble tip of the red giant branch value is 21.7. The Webb value, using the same method on the same galaxy, is 17.6. Those are formally inconsistent with each other. 40 orbits of Hubble time and the sharpest infrared instrument ever flown disagree about how far away this object is, and the authors of the 2026 paper state plainly that uniform Webb imaging of the remaining candidates is critically needed. That same paper did settle one thing in the Discovery team's favor. The candidate galaxies all sit at about 20 megaparsecs and are not members of a foreground group at 13, which kills the chance alignment objection even as it reopens the exact distance. Here is the part that is usually reported wrongly, and it is the reason this item belongs on a list of things nobody can explain rather than a list of surprises. The paradox damages both competing theories. Start with modified gravity, the family of ideas in which dark matter does not exist at all, and instead the law of gravitation behaves differently at very low accelerations. Those theories were built to explain exactly the observations dark matter was invented for: galaxies rotating too fast for their visible mass. And in those theories, the low acceleration behavior is not optional. It is an unavoidable consequence of ordinary matter being present. Put stars somewhere, and the modified behavior appears. It should always be detectable. So a galaxy where it is not detectable is precisely the observation the theory is not supposed to permit. This was reported, correctly, as a serious problem for modified gravity. Advocates responded by developing a formulation in which a small galaxy sitting close to a much larger neighbor has its own internal gravity weakened by the external field, an escape route that works, but only if the galaxy lies within a particular distance of that neighbor. Which returns the entire argument to the distance nobody has pinned down. Now take standard cosmology, in which dark matter is a real substance. That framework has an equally serious problem, and it gets far less coverage. No theory of galaxy formation produces a galaxy without a dark matter halo. The halo is supposed to come first. Dark matter clumps under gravity, forms a well, ordinary gas falls into the well, and stars form at the bottom of it. That is the standard picture of how every galaxy in the universe assembled. A galaxy with stars and no halo is not something anybody's model produces. Co-author Alison Merritt put it as plainly as it can be put. There is no theory, she said, that predicts these types of galaxies, which is a genuinely unusual situation. Most anomalies favor one side of an existing argument. This one is a problem for everybody. There is a proposed origin, and it is testable, which is what makes the following 4 years interesting. In 2022, Van Dockum and colleagues published in Nature a mechanism they called a bullet dwarf collision. Two gas-rich dwarf galaxies collide at high speed, roughly 8 billion years ago. In such a collision, the dark matter of each galaxy passes straight through the other, because dark matter interacts only through gravity and does not collide with anything. The gas, however, does collide. Gas slams into gas and stops. So the dark matter keeps going, and the gas is left behind, stranded in the middle. Then stars form out of that stranded, shocked gas. The result is galaxies made entirely of ordinary matter that were never inside a halo at all. The prediction that follows is specific. Such a collision should leave a line. The two dark matter halos continue outward in opposite directions, and the ordinary matter galaxies form in between. And there is a line. DF2 and DF4 sit inside an apparent linear structure of 7 to 11 large, faint objects, forming a trail more than 2 megaparsecs long, angled about 7 degrees from our line of sight. The highly dark matter-dominated remnants of the two original galaxies are tentatively identified at the leading edges. In 2025, that prediction was tested kinematically. A team measured radial velocities for 7 more galaxies along the trail, using 3 different observing modes at Keck, including one that treats the telescope simply as a light bucket, reaching effective surface brightnesses as faint as 28.6 magnitudes per square arcsecond. That is fainter than the natural glow of an apparently empty sky. 5 of the 7 followed the predicted velocity trend, a pattern with roughly a 2% chance of arising by accident, and the trail's velocities sat significantly above those of the surrounding group, marking it as a separate system moving through. On the 16th of June 2026, Yale announced a third confirmed dark matter-free galaxy on the trail, designated DF9. Keck spectroscopy gave a stellar velocity spread of 6.5 kilometers per second, consistent with the 8.3 expected from its stars alone, and far below the 24 expected if it carried a normal halo. Michael Keim, the Yale graduate student who found it, after it had been misidentified in a catalogue as a supermassive black hole, described the significance without overstating it. A line of galaxies lacking dark matter, he said, has never been seen before. There is something worth pausing on in that. Dark matter has been an inference for 90 years. It has never been seen. It has never been captured in a detector, despite decades of increasingly sensitive experiments buried in mines and under mountains. Everything anyone knows about it comes from watching what it does to things that are visible, the speeds of stars in galaxies, the bending of light around clusters, the pattern of ripples in the microwave background. And here, for the first time, the thing being measured is its absence. Not its effects, its non-effects. A quantity that has only ever been detectable through what it does is being detected by the fact that it is not doing anything. And the absence is arranged in a line, 2 megaparsecs long. pointing back at a collision that happened 8 billion years ago. Keim drew out the implication, and it is the sharpest argument in the whole affair. If stars and galaxies can form outside dark matter halos in extreme events, then dark matter is a physical substance that can be separated from ordinary matter and left somewhere else. Which is very difficult to reconcile with the idea that it is not a substance at all, but a modification of gravity. Gravity cannot be left behind. Matter can. The alternative reading has not gone away. A separate team has argued that DF4 is being tidally disrupted by a massive neighbor, detecting tidal tails containing about 7% of its stellar mass and an aligned distribution of globular clusters. That interpretation removes the need to revise anything at all, and its authors framed it that way explicitly. And a 2025 reanalysis of archival data raised DF2's confirmed globular cluster count from 10 to 16. The clusters are old, over 9 billion years, with a wide spread in composition. But the velocity spread they give depends on a single object. Include all 16, and it comes out at 14.9 kilometers per second. Treat the single highest velocity cluster, measured from a low-quality spectrum, as an unrelated interloper, and it comes out at 8.6. One faint smudge, at the edge of what the instrument can measure, is the difference between a galaxy with no dark matter and a galaxy with some. A galaxy that is missing its dark matter is strange enough. The next item on this list is a black hole that appears to have left its galaxy entirely and to have dragged a scar across 200,000 light-years on its way out. Number 4. The black hole that left a 200,000 light-year scar. Peter van Dokkum was not looking for this. He was searching archival Hubble images for globular clusters around a nearby dwarf galaxy, which is routine work, and there was a straight line running across the frame. His first assumption was the ordinary one. Cosmic rays strike spacecraft detectors constantly, and they leave straight, bright streaks. Every astronomer who has ever worked with space telescope data has seen thousands of them. There is automatic software whose entire job is to identify and remove them. The software did not remove it. The line was still there. His own account of the moment is the most human sentence in the entire affair. "This is pure serendipity that we stumbled across it," he said. I immediately thought, oh, a cosmic ray hitting the camera detector. The discovery paper by Van Dokkum, Imad Pasha and colleagues appeared in February 2023 under the title "A Candidate Runaway Supermassive Black Hole Identified by Shocks and Star Formation in its Wake." Follow-up spectroscopy came from 2 instruments at the Keck Observatory on Mauna Kea. What they had was a linear feature extending 62 kiloparsecs, about 200,000 light-years, outward from the nucleus of a compact star-forming galaxy whose light has been traveling for roughly 7.5 billion years. NASA's description of the scale was that the streak is twice the diameter of the Milky Way. That is not a decoration on a galaxy. That is a structure larger than the galaxy it is attached to. It is also nearly half as bright as that entire galaxy, which is an extraordinary property for a wake to have. Wakes are supposed to be faint disturbances. This one is competing with its source. The emission line ratios along its length indicate a mixture of star formation and fast shocks, and it terminates in a bright knot of ionized oxygen. But the detail that made the interpretation compelling is the age gradient, and it runs backwards. The stellar colors vary along the feature in a way best fitted by stellar age, increasing steadily with distance from the tip. The youngest stars are at the far end, away from the galaxy. The oldest are nearest to it. Think about what that means. Anything streaming out of a galaxy should get older as it gets further away, because it left earlier. Material at the far end has been traveling longest. This structure does the opposite. Star formation is happening most vigorously at the outermost end, hundreds of thousands of light-years from the galaxy, in gas that should be far too thin to form anything. Unless something is out there, moving, compressing the gas ahead of it as it goes. The best fit time since ejection was about 39 million years, which implies a velocity of roughly 1,600 kilometers per second. The black hole mass was quoted in press materials as up to 20 million solar masses, though it should be said clearly that this figure was never directly measured, and that the same press release circulated in a second version quoting 10 million instead. 1,600 kilometers per second is difficult to hold in the head, so it is worth an anchor. NASA's own release phrased it as fast enough to travel from Earth to the Moon in 14 minutes, though that figure does not actually follow from 1,600 kilometers per second, which would cross that distance in about 4. It is press copy rather than physics, and it is a useful reminder to check the arithmetic in a release, rather than inherit it. The correct comparison is that this object crosses the distance from the Sun to the Earth in a little over a day, and it has been doing so continuously for 39 million years. The feature is also not perfectly straight in the Hubble images. It wavers slightly along its length, and the 2023 paper argues that the amplitude of that wobble is itself consistent with the runaway interpretation. An object moving through a lumpy medium should not carve a perfectly ruled line. The proposed mechanism in 2023 was a 3-body slingshot, and it is worth understanding because it is one of the few places where the chaos of gravity produces something this dramatic. 2 galaxies merge. Each carries a supermassive black hole at its center, and those 2 black holes eventually settle into orbit around each other, forming a binary. Then a 3rd galaxy arrives, with a 3rd black hole. 3 massive bodies in a bound gravitational system is a famously unstable configuration. There is no general stable solution. What happens instead is that the system redistributes energy until one object is thrown out. One black hole extracts momentum from the other 2 and departs at enormous speed, while the surviving pair recoils the opposite way. Van Dokkum's paper reported a fainter, shorter counterfeature on the opposite side of the galaxy, marginally detected, possibly shocked gas trailing behind the departing pair. And there is a piece of supporting circumstantial evidence. There is no sign of an active black hole remaining at the host galaxy's core. The ejection of supermassive black holes from galactic centers was theorized in 1974, roughly 50 years before anything resembling an observation of one. Van Dokkum framed it that way himself. "We have known for a long time that supermassive black holes exist," he said, and it had been predicted for about 50 years that they could sometimes be ejected from galaxies. It is worth trying to picture what the object would actually be, because the wake is the only visible part, and the wake is not the thing. The black hole itself is invisible. It is not accreting much, so it produces very little light of its own, and at that distance, it would be a point far below the detection threshold of any instrument. What you would see, if you could position yourself alongside it, is the gas. Ahead of it, thin intergalactic gas is being compressed. Not by contact, nothing touches anything out here, but by the gravitational disturbance of tens of millions of solar masses passing through at hundreds of kilometers per second. The gas piles up in front, the way water piles up in front of a hull. It heats. It becomes denser than it has been in billions of years. And behind it, that compressed gas begins to collapse into stars. Not a few. Enough to be seen from 7.5 billion light-years away. A trail of new stars unspooling behind an object that is producing no light at all, marking a path across 200,000 light-years of empty space, with the newest stars at the leading edge and the oldest ones far behind, near the galaxy the object abandoned. The bright knot at the far end was never explained, even by the people who found it. In 2023, it was interpreted as either gas shocked and heated by the black hole's supersonic passage, or as radiation from an accretion disk around the black hole itself. Those are very different things. One is the road, the other is the vehicle. Van Dokkum said so outright at the time. How it works exactly, he said, is not really known. And the counterfeature, the fainter structure on the opposite side, which the three-body picture requires, because the surviving pair has to recoil somewhere, was only ever marginally detected. It is one of the two features the deep 2024 imaging went looking for and did not find. Neither camp has publicly reconciled that non-detection with the 2025 claim of kinematic evidence for a bow shock. The imaging says the bow shock is not visible. The spectroscopy says it is moving. Both statements are in print. If it is real, because within 2 months of the announcement, a group at the Instituto de Astrofísica de Canarias published a paper whose title is simply The Question: Supermassive Black Hole Wake or Bulgeless Edge-on Galaxy. Their argument was disciplined, and it has never been refuted. First, the feature's position-velocity curve looks like an ordinary galaxy rotation curve, peaking near 110 kilometers per second. Second, its stellar mass and rotation place it on the Tully-Fisher relation, which is the tight empirical relationship that ordinary rotating disk galaxies obey, and other things generally do not. Third, its length, width, and brightness profile closely match a well-known nearby galaxy that is bulgeless and seen edge-on. In other words, this may not be a wake. It may be a perfectly ordinary thin galaxy that happens to lie in the same line of sight, seen precisely edge-on, so that it appears as a straight line next to something else. They followed with an order of magnitude analysis, arguing that the disturbance a passing black hole imparts to surrounding gas is small and would require exceptional conditions to collapse into billions of solar masses of stars in only 39 million years. Van Dokkum answered with deeper imaging from the Very Large Telescope, showing the feature runs continuously to the compact galaxy with no gap, which he argued is difficult to reconcile with two unrelated objects. Then in 2024, the Canarias group returned with very deep new Hubble imaging, specifically targeting the two features the black hole scenario predicts, a bow shock at the head and the counterwake on the other side. They found neither. Their institutional release was headlined, "The Mystery of the Runaway Supermassive Black Hole, Solved." It was not solved. In December 2025, Van Dokkum and colleagues published Webb observations under the title "Webb Confirmation of a Runaway Supermassive Black Hole via its Supersonic Bow Shock." Using the integral field unit on Webb's near-infrared spectrograph, an instrument that produces a full spectrum at every point in the image rather than along a single slit, they found a sharp kinematic discontinuity at the tip. A change in radial velocity of about 600 kilometers per second across a tenth of an arcsecond, which is 1 kiloparsec. A velocity jump that abrupt is what a shock front looks like. Fitting a shock compression model to it gives a black hole velocity of 954 kilometers per second at an inclination of 29 degrees to our line of sight. The previously confusing decline in velocity along the length of the feature is explained as shocked gas being gradually entrained into the surrounding medium downstream, and energy conservation over the wake's lifetime implies a black hole mass above 10 million suns. The paper contains a sentence of unusual candor in its own author comments. The discovery paper, they wrote, was right about the key interpretation, but had quite a few of the details wrong. That is worth taking seriously, rather than treating as an embarrassment, because the details that changed are not small. The velocity dropped from 1,600 kilometers per second to 954. And the ejection mechanism changed entirely, from a three-body slingshot to gravitational wave recoil from a two-body merger. Those are different physical events, requiring different progenitor configurations. Both cannot be right. And then, on the 12th of February, 2026, the Canarias group replied, using the identical Webb dataset. Building diagnostic diagrams from the emission line ratios, the standard technique for distinguishing shocked gas from photoionized gas, they find that the TIPS ratios fall squarely on the locus occupied by low metallicity, low extinction regions of ionized hydrogen. Ordinary star-forming nebulae. A region of that diagram that does not overlap with where shocks in merging galaxies sit. Their conclusion is that the tip is an ionized hydrogen region inside an ordinary star-forming galaxy. So the state of play in 2026 is that two teams of competent professionals are analyzing exactly the same Webb data and reaching opposite conclusions, and neither has retracted anything. This is not a case where better data settled an argument. Better data made both cases sharper. And that is worth stating plainly, because the popular expectation of how science works is that ambiguity is a temporary condition cured by resolution. Sometimes higher resolution simply gives both sides more to work with. There is one further asymmetry in this dispute that is easy to miss. The black hole reading requires a specific, rare, finely tuned event. The galaxy reading requires only that two ordinary objects happen to line up from our particular vantage point, which over a sky containing 100 billion galaxies is not rare at all. Coincidences of alignment are the most common explanation in all of observational astronomy, and they are the first thing any careful astronomer tries to rule out. They do not even agree on the object's dimensions. The discovery paper gives 62 kiloparsecs long. The 2026 note gives about 45 kiloparsecs long and 1 kiloparsec wide. The mechanism the newer papers favor is worth understanding, because it is one of general relativity's stranger predictions, and it is not widely known. When two black holes merge, they radiate gravitational waves, ripples in space-time itself, carrying energy away. If the two holes have equal masses and aligned spins, that radiation is symmetric and everything cancels. But if the masses are unequal or the spins are misaligned, the radiation is not symmetric. More momentum leaves in one direction than the other. Momentum is conserved. So the merged remnant recoils. It is a rocket made entirely of ripples in space-time, and it has no exhaust, no fuel, and no moving parts. Typical recoils are around 100 kilometers per second, which is enough to displace a black hole within its galaxy, but not to remove it. Finely tuned configurations, with spins anti-aligned and perpendicular to the orbital plane, produce what the literature calls superkicks, of order 1,000 kilometers per second, with a theoretical maximum near 5,000. At those speeds, the remnant leaves the galaxy entirely and never returns. In July 2026, a paper in Physical Review Letters took the 954 km per second figure at face value and reconstructed the merger backwards. Their answer, a gravitational wave-driven black hole merger about 70 million years ago, with a precessing binary and a high spin on the more massive hole, which is what a kick that large requires. That reconstruction is elegant. It also depends entirely on a disputed measurement being real. This is not the first candidate, and none of the earlier ones ever resolved either. A radio-loud quasar, catalogued as 3C186, has a compact object offset about 11 kiloparsecs from its host galaxy's center, with a velocity offset of about 2,100 kilometers per second between its broad and narrow emission lines. It has been studied for over a decade. A 2024 conference presentation on it was titled, "With Admirable Honesty, Still Possible but Unlikely." A second long-standing candidate shows two distinct compact optical sources inside a single galaxy and a 1,300 km per second line offset, and remains ambiguous between recoil, a slingshot, and simply being a pair of active black holes a kiloparsec apart. What is not in dispute is that the physics is real at smaller scales. Direct evidence that large kicks occur in nature was published in 2022 from a stellar mass black hole merger detected in gravitational waves. And in 2025, a paper showed that higher-order gravitational wave modes allow the kick direction of a real detected merger to be constrained. So for stellar mass black holes, the recoil is now a measured quantity. For supermassive ones, it remains entirely inferred. Simulations suggest these objects should be common. Cosmological modeling indicates that a galaxy the mass of the Milky Way hosts on average about a dozen supermassive black holes, most of them wandering the halo rather than sitting in the nucleus. Thousands are expected in the halos of galaxy clusters. If those numbers are right, wandering black holes are ordinary, and the only rare thing is the wake. There is a third explanation in the literature that almost nobody discusses, distinct from both readings. A 2023 modeling paper showed that flyby encounters between galaxies involving multiple black holes can produce star-forming linear wakes without any ejection at all. NASA named the Nancy Grace Roman Space Telescope as the instrument most likely to find more of these streaks, and noted that doing so will probably require machine learning shape detection across enormous survey volumes, because nobody can search for them by eye. Which is a quiet acknowledgement of how this one was found in the first place. A person looked at an image for a different reason and noticed something odd. Imad Pasha, the graduate student co-author, described the experience in terms rarely found in a press release. Going from noticing the streak and thinking, "Hey, that is weird," to this paper, he said, was so incredibly fun and satisfying as we were all learning every step of the way. Whichever side turns out to be right, the honest position is that the sharpest telescope ever built has now looked directly at this object, and two teams came away certain of opposite things. Which is, in the end, what an unexplained result actually looks like from the inside. Every item so far has been a single object. From here, the list stops looking at things and starts looking at populations. Number 3. The galaxies that arrived too early. The James Webb Space Telescope was built, more than for any other single purpose, to see the first galaxies. The expectation going in was well-founded and widely shared. 30 years of theory and Hubble observation pointed to the same picture. The earliest galaxies would be small. They would be faint. They would be chemically primitive, made of almost pure hydrogen and helium, because nothing had yet had time to manufacture anything heavier. They would be structureless, no arms, no bars, no organized rotation, just irregular clumps. And they would be rare, because in a young universe there simply had not been enough time to assemble many of them. Within months of first light, Webb began returning early galaxies that were too bright, too numerous, too chemically enriched, and in some cases already finished forming stars entirely. The story that reached the public first was the one about universe breakers, and the honest version of it is the correction rather than the claim. In February 2023, Nature published a paper by Ivo Labbé and colleagues from the KEARS survey, reporting 6 candidate galaxies at redshifts between 7.4 and 9.1, roughly 500 to 700 million years after the Big Bang, with inferred stellar masses above 10 billion suns. One candidate came out near 100 billion, comparable to the entire present-day Milky Way, at a moment when the universe was about 4% of its current age. The masses came from photometry alone, using a limited set of filters. Which is to say, from brightness measurements across a handful of wavelengths fitted to models of what a population of stars should look like. That is a legitimate technique. It is also one with well-known degeneracies, and Labbé's team flagged the risk explicitly in the paper. For the most massive candidate, they wrote, model solutions with 10 to 200 times lower stellar mass could be obtained by changing the assumptions, and those solutions fit the data similarly well or better. That caveat did not survive into the press coverage. What survived was the phrase, universe breakers. Spectroscopic follow-up, which measures actual redshifts and actual spectral features rather than inferring them, subsequently lowered nearly all the candidates below 30 billion solar masses. And one of them turned out to be something else altogether. It showed broad emission lines, with a width around 1800 kilometers per second, which is the signature of gas orbiting very close to a black hole at very high speed. The object hosts an accreting black hole of a few tens of millions of solar masses. Light that had been counted as stars was, at least in part, light from matter falling into a black hole, which is a much simpler resolution than revising cosmology, and it is the one that turned out to be right for that particular object. It is also worth knowing how small the sample was. The original selection contained 13 candidate massive galaxies, and spectra were obtained for 6 of them. The 6 famous objects were a subset of a subset, chosen from a survey covering a patch of sky you could cover with a grain of rice held at arm's length. That is not a criticism of the work. It is simply the scale at which frontier astronomy operates, and it is the reason results at this frontier move as much as they do. There is a companion story worth telling in full, because it is the best cautionary tale of Webb's first years. A galaxy catalogued as KEARS 93316 was identified photometrically as an extraordinarily bright candidate at redshift 16. If real, that would have placed it around 250 million years after the Big Bang, resetting every record at once. Spectroscopy found it at redshift 4.912 instead. Not slightly closer. Vastly closer. The difference between the universe being 250 million years old and being well over 1 billion. The cause was a rare conspiracy of properties. The galaxy has a red continuum, and it has extremely strong emission lines from oxygen and hydrogen. Those lines happen to fall inside one particular filter, boosting its brightness enough to mimic the abrupt drop in flux that marks the signature of a much more distant object. 2 unrelated features aligned to produce a false signal. The paper reporting this both confirmed 2 other candidates beyond redshift 11 and refuted this one, in a single stroke. Its title is exactly that, confirmation and refutation of very luminous galaxies in the early universe. So a substantial portion of the early alarm was real, and a substantial portion was measurement error being corrected in public at speed. That is worth stating clearly, because what survived is more than strange enough without exaggeration. What survived is this. A galaxy designated JWST-GS-Z14-0 was confirmed at redshift 14.32 after nearly 10 hours of continuous spectroscopic integration in January 2024. That places its light at about 290 million years after the Big Bang. It is spatially resolved, meaning Webb can see that it has an extent rather than being a point. Its half-light radius is 260 parsecs, giving a diameter over 1,600 light-years. Its absolute ultraviolet magnitude is near -21, which places it among the most luminous galaxies known at any early epoch. And its light is dominated by young stars rather than by an active black hole, which was checked precisely because of what had happened with the earlier candidates. Its stellar mass is around 500 million suns. That galaxy also holds a smaller record that says something about how far the instrument is being pushed. It was detected photometrically at 7.7 microns with Webb's mid-infrared instrument, which was the first mid-infrared photometric detection of any galaxy beyond redshift 14. Mid-infrared is where Webb is least sensitive and where the sky is hardest to work against. Getting a detection there at all of an object whose light left when the universe was 2% of its current age is close to the limit of what the observatory can do. It should also be said that the record for most distant galaxy has changed hands at least 4 times since 2022, and at least one of those records was retracted in between. The churn is not a sign of a field in trouble. It is a sign of a field working at the precise edge of its instrument, where the difference between a discovery and an error is a few photons in a filter. In May 2025, a team led by Rohan Naidu reported an object designated MOM-Z14 at a spectroscopic redshift of 14.44. That is roughly 280 million years after the beginning, and as of August 2026, it remains the most distant spectroscopically confirmed galaxy anybody has found. It is luminous. It is extremely compact, with an effective radius of 74 parsecs, a galaxy smaller across than the distance from the Sun to some of the nearer stars in our own neighborhood, multiplied a few hundred times. It is elongated, with an axis ratio of 1:4, which argues against a black hole dominating its ultraviolet output, because a black hole would appear as an unresolved point. Its ultraviolet slope is steep enough to imply essentially no dust at all. And its star formation rate rose roughly tenfold in the 5 million years before the light left it. It also shows nitrogen emission, with a nitrogen-to-carbon ratio well above the Sun's, an abundance pattern that closely resembles the globular clusters of the local universe and the most ancient individual stars in the Milky Way, which raises the possibility that what Webb is photographing at the edge of the observable universe is the formation of exactly the kind of ancient star cluster that still orbits our own galaxy today. But the number that should be dwelt on is none of those. It is this one. The density of bright galaxies at redshift 14 to 15, implied by the survey that found MOM-Z14, is 182 times larger than pre-Webb consensus models predicted. Not 80% more. 182 times more. Then there is the oxygen, and the oxygen may be the single most difficult result on this list to accommodate. In 2025, 2 independent teams using ALMA, an array of radio dishes in the Atacama Desert, detected an emission line from doubly ionized oxygen at 88 microns in JWST-Z14-0. The detection refined the galaxy's redshift to 14.1793, a precision improvement of roughly 180 times over the Webb value. It is the most distant detection of oxygen ever made. Combined with Webb photometry, the galaxy's metallicity works out at 5 to 20% of the Sun's. That is roughly 10 times more heavy elements than models predicted for that epoch. The significance of oxygen specifically is that there is only one way to make it. Oxygen is forged in the cores of massive stars and released when those stars explode. There is no other source. It is not left over from the Big Bang, which produced hydrogen, helium, and a trace of lithium, and essentially nothing else. So to have measurable oxygen inside a galaxy, you need at least 2 complete stellar generations. Stars have to form. They have to live. They have to die, violently. Their debris has to disperse, mix, cool, and be gathered into new stars that are bright enough to see. All of that has to happen inside a galaxy less than 300 million years old, in a universe that spent its first several 100,000 years too hot to make neutral atoms at all. It is worth slowing down on the size of that window, because 300 million years sounds like an enormous span, and in this context, it is not. In 300 million years, the universe has to cool out of an opaque fog of ionized plasma. Gravity has to gather the first clouds of neutral gas. Those clouds have to collapse, fragment, and ignite the first stars, which had no heavy elements to help them cool, and therefore should have formed slowly and with difficulty. Those stars have to burn through their entire lives. They have to explode. Their ashes have to be reincorporated into a second generation. And by the end of it, the galaxy is already 1,600 light-years across and bright enough to be picked up 13.5 billion years later by a telescope at a gravitational balance point beyond the Moon. 2 further results make the picture worse in a different direction. The first is that some early galaxies had already stopped. An object designated JWST-Z7-01-QU sits at redshift 7.29, about 700 million years after the Big Bang, and shows the spectral signature of a galaxy that has quenched. There is a Balmer break, indicating an aging stellar population, and there are no emission lines, indicating no ongoing star formation. It formed a burst of stars, and then it stopped. A second object, from the Rubies program, is a massive quiescent galaxy at essentially the same redshift, with a physical size of just 209 parsecs and a stellar mass surface density matching the densest quiescent galaxies found billions of years later. Its inferred number density is more than 100 times larger than any model predicts. And follow-up work found it sitting inside a large reservoir of cold gas while forming no stars at all. That is a genuinely bizarre state for a galaxy to be in. Cold gas is the fuel. Having the fuel and not burning it requires something actively preventing collapse, and nobody has identified what. A related result makes the quenching problem sharper. A massive quiescent galaxy confirmed at redshift 4.658 formed its stars over roughly 200 million years and had shut down by redshift 6.5. Which means the star formation happened and finished before the universe was 1 billion years old. The whole cycle, from ignition to exhaustion, compressed into a window shorter than the time it takes the Sun to complete 4 orbits of the Milky Way. Before these detections, the earliest known quiescent galaxies sat at about 1.2 billion years after the Big Bang. Webb pushed that boundary back by 500 million years. The second result is about shape. Spiral arms and central bars are not decorations. They are dynamical structures that require a settled, rotationally supported disk, a galaxy where the stars are moving in an organized, coherent way rather than on random orbits. Building that takes time. Mergers disrupt it. The early universe was supposed to be too chaotic for it. A barred spiral was confirmed at redshift 3, with a stellar mass around 4 billion suns, implying that bars could form in about 400 million years and that dynamically settled disks were already in place. A grand design spiral nicknamed Zhulong, meaning torch dragon, was found at photometric redshift 5.2, with a disk spanning over 60,000 light-years and more than 100 billion solar masses of stars. And in June 2026, a barred spiral candidate was reported at redshift 5.102, with a bar about 14,700 light-years long. Across all the surveys taken together, the number density of bright ultraviolet galaxies at redshift 9 to 12 runs 10 to 100 times above what was predicted before Webb launched. The candidate explanations are numerous, and the number of them is itself the problem. A field with 6 live explanations effectively has none. The first is that the initial mass function was different, that early star formation produced proportionally more massive, brighter stars, so the same amount of gas yields much more light. That is plausible because heavy elements are what allow gas to cool efficiently, and gas that cannot cool fragments into larger pieces. It is also completely untested. There is no direct measurement of the stellar mass function beyond redshift 10, and there may never be one. The second is that early galaxies simply converted a larger fraction of their gas into stars. The third is feedback-free starbursts. In sufficiently dense gas, stars form faster than supernova feedback can blow the gas away, so for a brief window nothing regulates the burst, and it runs to completion. The fourth is that star formation is bursty rather than steady. If galaxies flicker rather than shine continuously, any survey with a brightness cut catches them disproportionately during their bright phases and overcounts. The fifth is hidden black holes contributing light that gets counted as stars, which is already confirmed in individual cases. The sixth is that there was simply no dust to dim them, which is consistent with the steep ultraviolet slopes actually measured. And the seventh is cosmic variance. Webb survey areas are small and the universe is lumpy, and small samples of a lumpy thing can mislead. Supporting evidence for 2 of those explanations arrived together. A 2025 ALMA study of galaxies beyond redshift 12 reported low dust masses alongside high star formation efficiency, 2 separate candidate mechanisms pointing the same direction in the same objects. That does not settle which is dominant, but it does mean the 2 are not competing so much as compounding. None of the 7 explanations is mutually exclusive with the others, which is part of why the problem has been so resistant. If the true answer is that 4 of them each contribute a factor of 2, the total is a factor of 16, and no single mechanism will ever look like the culprit in isolation. Disentangling overlapping causes with small samples is one of the genuinely hard problems in observational science, and it is harder still when every sample takes 10 hours of the most oversubscribed telescope ever built. An analysis in April 2026 argued that systematic uncertainties in deriving stellar masses from spectral fitting and the asymmetric scatter those uncertainties introduce bring the inferred star formation efficiencies back toward model expectations. The current professional position is that the tension has narrowed substantially and has not closed. There are more exotic proposals in the literature: early dark energy, primordial black holes, cosmic strings, and it is worth being clear that none of them has observational support. They are model-fitting exercises rather than detections. Some of the JADE's record holders have also been claimed as consistent with objects powered by dark matter annihilation rather than fusion. That is a minority hypothesis with no consensus behind it, and it should be treated as such. One last detail belongs here, because it undercuts the neatest version of the early universe picture. A galaxy at redshift 13, about 330 million years after the Big Bang, showed a hydrogen emission line that should have been absorbed completely. At that epoch, the intergalactic medium is supposed to have been almost entirely neutral, and neutral hydrogen is extremely efficient at absorbing exactly that wavelength. The line was there anyway. And MOM-Z14 shows no strong absorption wing either, tentatively implying its surroundings were already partly ionized at a redshift where essentially every model says the universe was completely opaque. Some of the light Webb has been counting was never starlight at all. The next item is what happened when astronomers looked directly at the objects that had been fooling everyone. Number 2. The little red dots. In December 2022, less than 6 months into science operations, Webb's images began showing objects that were compact on the sky and strikingly red. They were nicknamed little red dots, and the name stuck because at the time nothing more precise could be said about them. They were dots. They were red. That was the extent of what anyone knew. What made them impossible to dismiss is that they surfaced independently across every major survey, SEERS, JADES, Uncover, and later others. Different observing programs, different fields of sky, different teams, different detectors. When a population appears in all of them, it is not an artifact of any of them. Formal characterization followed in 2023 and 2024 in papers led by Jorma Matthey, Jenny Green, and Ivo Labe. And the selection criterion that defines the class is peculiar in a way that turned out to be the first real clue. These objects are blue in the rest frame ultraviolet and red in the rest frame optical. Plot their brightness against wavelength and the line comes down steeply, turns a corner, and goes back up. It produces a distinct V shape. Nothing in the local universe looks like that. Dale Kochevsky at Colby College and colleagues compiled 341 of them from public web data, presented in January 2025. It is one of the largest samples assembled, and nearly all of the objects in it existed within the first 1.5 billion years after the Big Bang. The redshift distribution is the strangest demographic fact in modern extragalactic astronomy, and it is worth stating carefully. Little red dots appear in large numbers around 600 million years after the Big Bang. Their numbers rise. They peak, and then they decline rapidly around 1.5 billion years, after which they essentially vanish from the record. They account for a few % of galaxies above a characteristic brightness during their era, and at least 20% of all broad-line active galaxies in that window. Then they stop. Whatever these things are, the universe made a great many of them for about 1 billion years, and then stopped making them, and nobody knows why. They are also physically tiny. Typical effective radii are around 100 parsecs. A typical little red dot has a radius no greater than 500 light-years, and many are under 150. That is roughly 2% of the radius of the Milky Way. In a morphology study of 99 of them, 69 were purely compact, with no resolvable structure whatsoever, points at the resolution limit, and no more. The obvious first explanation for anything red in astronomy is dust. Dust scatters blue light preferentially and lets red through, which is why sunsets are red and why the plane of the Milky Way looks brown rather than white. Dust explains most red objects in the sky. Little red dots are not reddened by dust, and the evidence for that is specific and rather elegant. A 2024 analysis fitted broken power laws with a free inflection point to a sample of these red emitters, meaning the fit was allowed to put the corner of the V wherever the data preferred, without being told where to look. Every strong inflection landed at the same wavelength. 3,645 angstroms in the rest frame, which is the Balmer limit, the exact energy at which a hydrogen atom with its electron in the second energy level can be stripped. That is a hydrogen feature. Dust does not produce a break at a specific atomic wavelength. Dust produces a smooth, gradual slope, because scattering efficiency varies continuously with wavelength rather than jumping at a particular energy. A sharp corner at an atomic transition means atoms are doing it. That single observation reframed the entire question. These objects are not ordinary things behind a veil. Their light is being shaped by hydrogen in enormous quantities, sitting somewhere very close to whatever is producing it. Spectroscopy of more than 100 of them finds at least 70% with broad hydrogen emission lines, gas moving at roughly 1,000 kilometers per second, which is about 2 million miles per hour. Standard calibrations convert those line widths into black hole masses of 1 million to 100 million suns, which produced the second problem. In nearby galaxies, black hole mass tracks host galaxy stellar mass at roughly 1 part in 1,000. That relationship is one of the most cited empirical facts in extragalactic astronomy, and it is remarkably tight across 4 orders of magnitude. It implies that black holes and galaxies grow together, regulating each other, which is a satisfying idea, and one that a great deal of theory has been built on. Fabio Pacucci and colleagues found early black holes running 10 to 100 times more massive than that relation predicts, relative to their hosts. The most extreme case sits behind a galaxy cluster whose gravity bends its light into 3 separate images of the same object. Catalogued as Abell 2744-QS01, it lies at redshift 7.045, about 700 million years after the Big Bang, when the universe was 5% of its present age. Its black hole is roughly 50 million solar masses, and it contains about twice as much mass as all the surrounding galactic material combined. It has been described as a naked black hole, an object where the black hole is not sitting at the center of a galaxy so much as the galaxy is a thin residue around the black hole, a cloud of hydrogen and helium with barely any heavy elements in it, weighing half what the hole does. Now, if little red dots are simply obscured quasars, accreting black holes wrapped in dust, then 3 specific things should be true. None of them is. First, they should be bright in X-rays. Gas falling into a black hole heats to millions of degrees before it crosses the horizon, and hot gas radiates X-rays. It is one of the most reliable signatures in astrophysics. 2 independent studies, including one that stacked the signal from many objects together to beat down the noise, found the expected X-ray emission missing. NASA's counterargument is that at sufficiently high gas densities, X-ray photons become trapped and reprocessed before they escape, so weakness could still be consistent with extreme obscuration. That is a defense. It is not a detection. Second, they should show a dusty torus. Nearly every active galactic nucleus is surrounded by a thick donut of warm dust, heated by the accretion and glowing in the mid-infrared. It is close to universal. Webb's mid-infrared observations of little red dots come back flat, and ALMA fails to detect cold dust continuum around them. A 2025 study confirmed a deficit of both hot and cold dust in the most luminous examples. The torus is not there. Third, they should flicker. Accretion is turbulent, and active black holes vary in brightness on timescales from days to years. It is how many of them were identified in the first place. A 2025 study found no photometric variability at all across Webb's imaging, and its authors argued that this challenges the active galaxy interpretation outright. So the objects have the emission lines of an accreting black hole, and none of the other properties of one. The idea that has taken hold since 2024 is stranger than anything the field expected, and it came out of a single object. Anna de Graaf at the Max Planck Institute for Astronomy was working through roughly 60 hours of Webb spectroscopy in a survey of about 300 very red sources. One object stood apart from every other. They named it the Cliff. Its Balmer break is roughly twice as strong as any stellar population model can produce. That is worth reading twice. Not stronger than expected. Not at the high end of the range. Twice as strong as the theoretical maximum for any population of stars, of any age, with any composition, in any configuration. There is a ceiling on how sharp that feature can be, if stars are making it, and this object is well above the ceiling. Every model the team built failed. Massive star-forming galaxy, failed. Dust-shrouded active nucleus, failed. The spectrum could not be reproduced. Their conclusion, published in 2025, is that the break, the emission lines, and the hydrogen absorption are most plausibly explained by something called a black hole star. A black hole wrapped in gas so dense that the envelope behaves like a stellar atmosphere. On that reading, the continuum is intrinsically red because it is the spectrum of a photosphere, not because dust reddened anything. They called it the clearest evidence to date that at least some little red dots are not ultra-dense massive galaxies. A higher redshift analog was reported soon after, at redshift 7.8, modeled with a photoionization code and fitting strikingly well. It is worth trying to picture what such an object would be, because it has no analog in ordinary astronomy. There is a black hole at the center. Gas is falling into it, and as that gas compresses and shears, it heats and radiates enormously. In an ordinary quasar, that radiation escapes more or less directly, and what you see is an accretion disk, brilliant, variable, X-ray loud. Here the gas around it is so dense that the light cannot get out directly. Photons are absorbed and re-emitted, working their way outward through the envelope by random steps. That process takes a very long time. The photon that finally leaves the surface has no memory of the shape or spectrum of the light that entered the envelope. It emerges thermalized, in equilibrium with the gas around it, which means the object has a surface, a photosphere, in exactly the sense a star has one. It has a temperature. It has a spectrum with hydrogen absorption features in it. And there is no fusion anywhere inside it. Not a single nuclear reaction. The entire luminosity comes from matter falling into a hole at the center, filtered through an envelope thick enough to make it look like starlight. From 13 billion light-years away, it looks like a star. It is a black hole wearing one. Theoretical support arrived quickly. Work by Kohei Inayoshi and Roberto Maiolino showed that sufficiently dense gas can produce a non-stellar Balmer break. Further papers modeled the envelopes directly. And in 2026, Mitchell Begelman and Jason Dexter argued that little red dots are quasi-stars, a seed black hole accreting far above the usual limit, inside a convective envelope held up by radiation pressure. Their predicted lifetimes are tens of millions of years. Set that against the observed number density, and the implication is that most or all supermassive black holes pass through this phase. Which would mean the little red dots are not an anomaly at all. They would be the missing childhood of every supermassive black hole in the universe, including the one at the center of the Milky Way. Then, in January 2026, a paper in Nature reframed the entire field again. Analyzing 12 individually studied objects plus 18 more, Rusakov, Watson, Brammer, Heinz, and colleagues argued that the broad emission lines are not broadened by the motion of orbiting gas at all. They are broadened by electron scattering. photons bouncing off free electrons in a dense ionized cocoon on their way out, each collision shifting the wavelength slightly, smearing a narrow line into a broad one. The line is wide, but nothing is moving fast. If that is right, the narrow intrinsic line cores imply black hole masses of 100,000 to 10 million suns, about 2 orders of magnitude lower than the virial estimates that hundreds of papers have been built on. The overmassive black hole problem would shrink dramatically. Not vanish, but stop being a crisis. 6 months later came a result from the opposite direction, and it is the most quietly deflating one. In July 2026, Pierluigi Rinaldi and colleagues, including Pacucci and George Riche, analyzed a spiral galaxy at redshift 2, nicknamed the Saguaro. It has a compact red nucleus with little red dot properties, brighter in the ultraviolet and infrared than in visible light, with weak but detected X-ray emission from a heavily obscured active nucleus. Then they did something clever. They artificially redshifted the image, degrading and dimming it to simulate how the same object would look if it were far more distant. The host galaxy vanished. Only the dot remained. Their conclusion is that little red dots may not be a unique population at all, but a temporary obscured phase of highly active black holes, and that their apparent uniqueness is partly an observational bias. We cannot see the host galaxy, so we conclude there is barely a host galaxy. The spiral arms were always there. They were simply below the threshold. Underneath all of this sits the oldest unsolved problem in black hole astrophysics, and it is the reason this item is worth 3,000 words rather than 300. Where did supermassive black holes come from? 2 families of answer compete. Light seeds, 10 to 100 solar masses, the collapsed remnants of the first generation of stars, which then have to grow by a factor of 1,000,000 or more, very fast. Or heavy seeds, 10 to 100,000 solar masses, formed by the direct collapse of a gas cloud that never fragmented into stars at all, skipping the stellar stage entirely. The observations that bear on this are exactly the ones on this list. A heavily obscured X-ray quasar was detected behind a cluster at redshift 10.1, about 470 million years after the Big Bang, implying a black hole of roughly 40 million solar masses in a host galaxy of comparable mass. It was presented as evidence for direct collapse. That claim was itself revisited and challenged in 2026. GN-Z11, at redshift 10.6, hosts a black hole of about 1.6 million solar masses, identified through emission lines tracing gas densities above 1 billion particles per cubic centimeter. And the most distant broadline active nucleus known is a little red dot at redshift 9.288, 500 million years after the beginning, with an inferred black hole mass around 10 to the 7.58 solar masses and a prominent Balmer break supporting the dense gas picture. Standard growth from a stellar remnant, at the maximum rate that radiation pressure allows, cannot produce those masses in that time. Something else happened in the first 500 million years. And the little red dots are by far the largest population of candidate witnesses to it. The alternatives have not been exhausted either. Mid-infrared survey work showed that many of these spectral energy distributions can be fitted by clumps of hot young stars in dense, dusty regions, obscured at the 90 to 95% level, no black hole required. A paper published in July 2025 proposed instead that they are supermassive metal-free stars of roughly 1 million solar masses, observed in the last few thousand years of their lives. A star of 1 million solar masses would be the largest single object ever to have shone anywhere. Another model has them as rapidly growing black holes reddened by extended dusty outflows rather than a static torus, which would explain why the infrared signature looks wrong. Local analogues have turned up, which is encouraging for anyone who wants this solved. 7 broadline objects with the same V-shaped spectral signature were identified among a parent sample of 2,190 nearby compact galaxies, and they also host overmassive black holes. Similar objects have been found in ground-based survey data and interpreted as a later evolutionary stage. And a black hole star candidate has now been reported as low as redshift 1.7, with an extreme Balmer break and broad absorption from thick winds. That is a target that can be studied in far more detail than anything at redshift 8. The evidence that at least some of them host real accreting black holes arrived early and has not been overturned. A broadline active nucleus was identified at redshift 8.5 in one of the lensing cluster surveys back in 2023, a demonstration, before any of the exotic models existed, that objects of this class at extreme distance can contain something feeding at their centers. And at least one of them, at redshift 7.3, sits inside an overdensity of 8 neighboring galaxies, which means they are not uniformly isolated. Some of them occupy crowded regions, which is where the gas supply would be. There is also a parallel puzzle in the very same data that suggests the problem may be broader than this one population. Work using the same survey confirmed that quiescent galaxies at moderate redshift are about 10 times more numerous than originally estimated. 2 separate categories of object, in the same fields, measured by the same instrument, both turning out far more common than the models allow. When 2 independent overcounts show up in one data set, the sensible first suspicion is not 2 separate physical surprises. It is that something in the modeling is shared and wrong. The leading explanation for why they disappear is inside-out growth. As star formation spreads outward from the nucleus, less gas is delivered to the center, the cocoon is shed, the object turns blue, and it stops qualifying as a little red dot. That is a hypothesis. It has not been measured. And there is a caveat that undercuts even the most basic property. Documented limitations in fitting morphologies to these objects mean that their famous compactness carries real measurement uncertainty. The sizes are effectively upper limits, derived by fitting models to sources only a few pixels across. One of the defining characteristics of the class may partly be a statement about the telescope rather than about the objects. Every item on this list so far has been an unexplained thing inside the universe. A structure, a moon, a star, a shortfall of light, a pair of worlds, an absent halo, a moving black hole, a population of early galaxies, and now a population that looks like stars and is not. The last item is an unexplained thing about the universe. Number 1. The universe that leans one way. The result at the top of this list is a count. That is all it is. And the count is the whole thing. Lior Shamir, an associate professor of computer science at Kansas State University, applied image analysis to galaxies in the JWST deep field, the same survey that produced several of the record-holding early galaxies you have already heard about, using Webb imaging at 3 wavelengths. 263 galaxies had an identifiable direction of rotation. 105 of them rotate counterclockwise. 158 of them rotate clockwise. Assuming the direction of rotation is random, which is what every version of standard cosmology requires, the probability of a split that lopsided or worse arising by chance is about 7 in 10,000. 3.39 standard deviations. The paper was posted in February 2025 and published in the monthly notices of the Royal Astronomical Society. There is an orientation detail that most popular coverage gets wrong, and it matters enormously for what follows. In Shamir's framing, clockwise means rotating opposite to the Milky Way, and counterclockwise means rotating the same direction as the Milky Way. So 158 galaxies are turning against us, and 105 are turning with us. That is roughly 50% more spinning one way than the other, and the direction that wins is defined relative to our own galaxy. Hold on to that, because it is the hinge. First, how you determine which way a galaxy is turning from a still image, since you obviously cannot watch it move. Spiral arms curve. They curve in a particular direction relative to the rotation, and the reason is that the inner parts of a galaxy orbit faster than the outer parts, so any disturbance in the disk gets wound up into a trailing spiral. The arms trail behind the rotation, the way the wake behind a boat trails behind the boat. So if you can see which way the arms curve, you know which way the galaxy turns. Shamir's method is not a neural network, and it is not human eyes, and both of those exclusions turn out to matter. Each galaxy image is transformed into a radial intensity plot, 35 by 360. Because spiral arms are brighter than the gaps between them at any given radius, a peak detection algorithm picks out the arm pixels line by line, and the sign of the slope through those peaks tells you which way the arms curve. There are two hard thresholds. A galaxy needs at least 30 detected peaks and a regression slope of at least 0.35, or it is discarded as having no identifiable direction. That is why only 263 galaxies survived out of a field containing far more. The inference from arm shape to spin rests on arms trailing rather than leading, which is overwhelmingly the case. There is a known counterexample, a galaxy called NGC 4622 with leading arms, and the paper calls such cases extremely rare. The one control described is a mirror test. The entire field was flipped and reanalyzed, and the results came out exactly inverse, which is what a directionally unbiased algorithm should do. It is worth knowing that this is not an isolated paper from someone who wandered into the field. Shamir has been making versions of this measurement for over a decade, across the Sloan Survey, Pan-STARRS, the Dark Energy Survey, Hubble, and the DESI Legacy Imaging Survey, that last one using 1.3 million annotated galaxies. His claim that the asymmetry axis sits near the galactic pole comes from mapping the imbalance across hemispheres, centered on every integer coordinate combination across the whole sky. His earlier Webb work is also worth recording, because it includes a result that cuts against him, and he reports it anyway. Applying the same method to a small field, he found 23 or 24 of 33 galaxies rotating opposite to the Milky Way. But applying it to Webb's very first released deep field returned a null result, 21 one way, 19 the other. He notes that this is expected under his own model because that particular field does not sit near a galactic pole. Whether that is a genuine prediction or a post hoc accommodation is exactly the kind of question an independent replication would settle. His paper contains a section whose title is effectively a rebuttal chapter aimed at the null result literature, a summary of experiments suggesting the distribution of galaxy rotation directions is random. That is unusual to see in a research paper, and it tells you how entrenched the argument had already become before Webb entered it. Now, why should anyone care about a count of 263 galaxies? Because of what it would violate. The cosmological principle has two halves. Homogeneity says the universe has the same properties everywhere on large scales, no special places. Isotropy says it looks the same in every direction, no special directions. Isotropy is not a minor technical assumption that could be relaxed without consequence. It is built into the equations used to derive the age of the universe. It underpins the expansion history, the interpretation of the cosmic microwave background, and essentially every cosmological distance anyone has ever quoted, including several you have heard in this video. In an isotropic universe with no preferred axis, galaxy spin directions should be a coin flip. There is no mechanism to make them anything else. Galaxies form from local collapses of gas, each one acquiring its rotation from the tidal torques of its own neighborhood, and those neighborhoods should have no idea which way any other neighborhood is turning. Shamir's claimed dipole axis peaks near the galactic pole, and the Jade's field lies close to it. He offered two explanations, and it is important to say that he offered both, and that he raised the objection to one of them himself. The first is that the universe has a preferred rotational axis. This is not a new idea, and it has a respectable pedigree even if it has never had evidence. Kurt Gödel found an exact rotating universe solution to Einstein's field equations in 1949. It is a real solution to the real equations, and it permits closed time-like curves, paths through space-time that return to their own past. Gödel, who was a close friend of Einstein's at Princeton, used it to argue against Einstein's own picture of time. The related family of ideas is black hole cosmology, in which our universe is the interior of a black hole sitting in some larger parent universe. Since black holes rotate, a universe inside one might inherit that rotation. The mechanism usually cited comes from work on gravity with torsion, in which the coupling between particle spin and the geometry of spacetime becomes repulsive at extreme densities, preventing a singularity from ever forming and instead producing a closed, nearly flat universe on the other side of each horizon. It should be said clearly that this is a long way outside mainstream cosmology, and its problems are serious. Paul Sutter separated the two ideas carefully in an essay in April 2025. Even a genuinely rotating universe, he pointed out, has only a weak connection to the universe inside a black hole picture because the Big Bang was a moment rather than a place, and because our universe expands while a black hole interior collapses. Those are opposite behaviors. There is also the white hole problem. Torsion-based bounce models require a bridge to a white hole on the far side, and white holes are catastrophically unstable. Drop a speck of dust onto one, and it converts back into a black hole. That instability is one of the standard reasons cosmologists do not take the picture seriously. And there is a numerical coincidence that this whole family of speculation hangs on, which deserves to be named and then handled carefully. The radius of the observable universe is close to the Schwarzschild radius corresponding to its estimated mass. That was noted independently by a physicist and a mathematician in 1972. It is a real coincidence. At least one cosmologist regards it as nothing more than that, and there is no established reason it should be anything more. The second explanation is, in its way, more disturbing, precisely because it is mundane. Because of the Doppler effect, a galaxy rotating opposite to the Milky Way's own rotation should appear very slightly brighter to us than one rotating the same way. The side of the galaxy moving toward us is boosted. The geometry works out marginally differently depending on the relative sense of rotation. If galaxies rotating against us are slightly brighter, we detect slightly more of them near our detection threshold. And the effect would peak near the galactic pole, which is exactly where Shamir's dipole sits. Shamir raises the fatal objection to this himself in the paper. The effect of rotational velocity on brightness is mild, he writes, and is not expected to lead to anything like a 50% difference. But look at what it would mean if it were somehow real. It would mean that the apparent brightness of a galaxy carries a systematic error depending on which way that galaxy happens to be turning relative to ours. And brightness is how distances are measured out there. Nearly every distance beyond the reach of parallax and standard candles ultimately traces back to how bright something appears. Which would mean the depth of the universe has been measured slightly wrong, for a century, in a way nobody noticed, because nobody thought to sort the measurements by rotation direction. Shamir explicitly links this to the disagreement over the expansion rate and to Webb's overabundance of massive early galaxies. If the second explanation is right, some of the other unexplained results on this list might be symptoms of the same error. So here is where the finale actually lands, and it is not where most coverage puts it. The interesting thing is not that the universe might be spinning. That is the less likely of the two options, and it comes with a stack of theoretical problems that its own advocates acknowledge. The interesting thing is that the two available explanations are the universe has a preferred direction, or we have been mismeasuring the depth of the universe for 100 years in a way that depends on which way galaxies happen to turn. There is no third option on the table that leaves everything intact. Either the geometry is wrong, or the ruler is. That is the payoff of this list, and it should be sat with rather than rushed past. But it should also be handled honestly, because this claim has been made before, and it has been wrong before, in a way that is genuinely instructive. In 2011, Michael Longo at the University of Michigan analyzed 15,158 spiral galaxies from the Sloan survey and reported a dipole asymmetry with a chance probability of about 8 in 10,000. Very nearly the same significance Shamir reports, from a sample 57 times larger. But the cautionary tale is Galaxy Zoo, and it is one of the best experiments ever run in observational cosmology. In 2008, a team classified roughly 37,000 Sloan spirals using public volunteers, ordinary people, looking at images on a website, saying which way the arms curled. The raw results showed a handedness signal. Then they ran the control. They showed volunteers mirrored versions of a subset of about 11,000 images and compared the answers. The volunteers had a bias. Human beings, it turns out, are slightly more likely to perceive a faint spiral as counterclockwise than clockwise. The numbers are worth quoting precisely because they are so small. Counterclockwise classifications fell from 6.032% to 5.942% once the images were flipped. Clockwise rose from 5.525 to 5.646. That is about 1/9 of a percentage point. And it had produced a statistically significant, sky-wide cosmological anomaly out of nothing at all. Once corrected, the winding directions were consistent with statistical isotropy. No dipole. No preferred handedness. In 2017, an automated study characterized and corrected the same bias independently. A real signal, in a large dataset, generated entirely inside the human visual system. That is what the field learned, and it is why nobody in this area accepts a spin asymmetry without a control. Independent groups have looked at Shamir's claim and disagreed. A 2024 analysis gathered every publicly available spin catalog and ran both Bayesian and frequentist multipole inference, finding no significant dipole and no monopole differing from a coin flip in any dataset. A companion note applied Bayesian analysis to a different large survey and reported what it called decisive evidence for the isotropic model, adding that Shamir's statistic lacks a strong theoretical foundation. Shamir replied to both, arguing that their method fails to detect asymmetry even in artificially biased test data. The clearest illustration of what is actually in dispute is a single catalogue of 139,852 galaxies. Standard binomial statistics on those numbers give a probability of about 6 in 100,000. The competing estimator, applied to exactly the same numbers, returns a result that is not significant at all. The fight is not about the images. Both sides agree on which way the galaxies curl. The fight is about which statistical estimator is correct for binary spin data distributed on a sphere, and that question does not currently have an agreed answer. There is prior work pointing both ways. An older manual catalogue of southern galaxy orientations, published in 1991, found 3,257 clockwise against 3,268 counterclockwise. Essentially perfect symmetry, from a sample 12 times larger than the Webb one. A 2020 study using a deep neural network on a different survey found 38,718 against 37,917, but the network's own classification error rate exceeded the size of the asymmetry, so the authors did not treat it as meaningful. When the measurement error is larger than the effect is not measurable. The sharpest public critique came from Sutter. Modern surveys have imaged roughly 100 million galaxies, he wrote, and this paradigm-shattering conclusion relies on 263 of them. His specific objection is the stack of selection cuts. One survey, one region of sky which happens to sit near the galactic pole. Face-on spirals only, since you cannot determine rotation direction from an edge-on disk. Then a discernibility filter requiring 30 peaks and a minimum slope. Each cut is individually defensible. Stacked, they define a very particular subpopulation, and the paper does not report what happens to the 158 to 105 split when those thresholds are varied. The paper also never states how many galaxies were rejected. The argument that a mirror-symmetric algorithm must reject symmetrically is an argument from first principles rather than a measurement, though Shamir did manually inspect the rejected galaxies and reported no discernible pattern among them. And it should be recorded plainly, as of August 2026, no independent group has reproduced the 263 galaxy measurement with a different pipeline. That is an open gap. It is not a refutation. There is one further thread in the paper that deserves to be flagged rather than repeated approvingly. Shamir links the anomaly to alternative models in which redshift is not caused by expansion at all, and to stars that appear older than the universe, including, by name, HD 140283, which is number 8 on this list. That connection should be handled carefully. Alternative redshift models sit far outside mainstream cosmology and have no observational support. But the fact that the connection is being drawn at all illustrates something about how these anomalies behave. Each one, taken alone, is a small discrepancy that a careful person can hold at arm's length. Assembled, they start reaching toward each other, and the reaching is not always disciplined. A star that measures a few 100 million years too old, a galaxy count that runs 180 times high, a spin split that should be a coin flip, and a 100-year-old assumption about brightness. It is very tempting to draw a line through them. Sometimes there is a line. Usually there is not, and the temptation is precisely what the mirrored image experiment was designed to guard against. There is a smaller detail in the Kansas State release that is easy to skip and is actually the load-bearing assumption of the entire second explanation. The Milky Way's own rotational velocity, it notes, had traditionally been considered too slow to matter compared with other galaxies. Everything in the Doppler bias reading depends on that traditional assumption being wrong. Not slightly wrong. Wrong by enough to produce a 50% effect from a mechanism nobody thought produced any effect at all. So why is this number 1, when the sample is small, and the statistics are contested. Because of the shape of the problem, not the size of the data set. Every other item on this list is an unexplained thing inside the universe. A structure in front of a dead star. A moon that may or may not be venting. A star that will not fit inside its own cosmos. A shortfall of light between galaxies. A pair of worlds with no sun. A galaxy without its dark matter. A black hole that left home. A generation of galaxies that arrived too early. A population of objects that look like stars and are not. This one is an unexplained property of the universe as a whole, and it is measured with an ordinary count that anyone with the data could check. It also has the cleanest resolution path of anything here. 263 galaxies is a small number, and Webb has already imaged far more. The measurement is reproducible in principle by any group with a different algorithm and a few weeks. The reason it sits unresolved is not that the test is difficult. It is that nobody has yet run it in a way that both camps accept. Which is, at the end of a list about the limits of 2 extraordinary telescopes, the most honest place to finish. Both of these instruments were built to answer questions, and they have answered a great many. The reason this list exists is that they are also good enough to find the places where the answers do not fit, the holes in a shell around a dead star, the plume that was never there, the star that keeps coming back too old, the 263 smudges that do not curl the way they should. An unanswered question is not a failure of an instrument. It is what a working instrument produces when it is pointed somewhere nobody has looked closely before. Sleep well, and good night.